Good morning, everyone. Buongiorno a tutti. Guten Morgen. Good morning. Good morning. So let's get started. Dear Thomas, dear Christoph, dear Mauro, dear colleagues, friends, a warm welcome here to this workshop on artificial intelligence and Earth observations from innovation to services. This event is organized jointly by DEFIS and CNECT with support from HaDEA and ECMWF and many others. My name is Michel Rixen from DEFIS Earth Observations Unit here at the Commission. We have an impressive 1,500 people registered for this event, and we're hoping to have the room full at least as well later today when people are arriving, and hopefully the strike is not putting too much constraints on people's arriving here. So this large turnout is demonstrating that the topic is really relevant and that it offers a lot of opportunities to us as well. And it's also an urgent topic that we need to address jointly between Earth observations and AI people. The turnout was a bit unexpected, actually, and this put also a bit of additional logistic constraints. So bear with us as well as we go along over these 2 days. Next slide, please. I will just provide a few housekeeping remarks. Yeah, thank you. Because of the large crowd, first, we want you to be safe. I'm not referring here to the Copernicus service or the emergency management service, of course, right? There are 3 exits. One is, of course, the one you came through the stairs, and otherwise there are 2 exits, left and right, from this room here. Another kind of emergency are the restrooms. There are some here on this floor, and as well up the stairs to the left at the entrance level. The main room is this auditorium. In principle, we will all fit here, but in case not, I will invite Commission people to join rooms 5A and 5B, which are the spillover rooms, in case that's needed. But we'll keep you updated. But for the time being, I think everyone is welcome to stay in this auditorium, and it will also facilitate the exchange and the Q&As and so forth. The meeting is also being broadcasted, and welcome also to our online participants. There is a slight delay of about 30 seconds or so, but I think that this is manageable. Coffee and lunch breaks will be served here in the foyer hall where you came through. There is also a nice cozy room to my left here, the VIP room, where speakers and moderators and panelists can also have a bit of a relaxing time if they want to. And coffee break will also be served, and lunch breaks will also be served at the entrance next to the gate where you came through. In case the rooms here get too crowded, I invite you to also to use that space so that we are not too packed here on this level. I would also kindly ask you to not bring food nor drinks in the demonstration room because that's a special room that was lent to us on a gentleman agreement. So please don't bring any food nor drinks in that room. Let's move now to the program. So we have quite a packed program. So that will consist of 8 plenary sessions over 2 days with keynote presentations and panel discussions and Q&As with the audience in person here, but also online. AI is, of course, a very vast topic, and there is only that much you can fit into a 2 days program. But we think that the program, tries to touch on, several aspects that the planning committee deemed was necessary to address especially for the Commission. We will request also the chairs to try to stick to the schedule because it's important to leave also time for the people who have a dedicated time for the demonstration. So there will be a small award for the sessions who finish on time. This is Swiss chocolate. So if you finish on time, you deserve this. Also, you know, the agenda, you know, I was hoping it would have been generated by an EU sovereign large language model, for example, that I would be an hologram, that all the speakers were avatars, that would be, you know, I would have said, you know, welcome to Copernicus 3.0. We're not there yet, but let's shape this AI and Earth observations world together. A reminder, the meeting is being recorded. Presentations will also be made available on the meeting webpage after the workshop. And there will be a summary published also on the meeting webpage, but that's going to come later, maybe in a few months from now. So, next slide. So for the Q&A, we'll take also, you know, from time to time questions from the audience, but I invite you also to grab the Slido QR code or the hashtag, and also keep that, especially for the people online. And during the different sessions, except for session 1, the chairs of each session will also prompt the audience from time to time, here in person and also online. So I think that was for the housekeeping. Let's now move to the heart of the program and session 1. You know, as I said before, the meeting is being organized jointly between CNECT and DEFIS, and we have the pleasure to have high representatives of both. So I will now pass the floor to my director, Christoph Kautz, Director for Space Policy, Satellite Navigation and Earth Observations. The short welcome will be done on behalf of our Deputy Director-General, Lorena Boax-Alonso. Christoph, the floor is yours.
Thank you very much. Good morning, dear ladies and gentlemen, colleagues, dear Thomas. It's a real pleasure to welcome you here today to this workshop on AI and Earth observation. And judging by the numbers of people who have inscribed, it seems to be a subject that is interesting for many of you, or many of us. And indeed, space is gaining more and more attention these days because of its strategic nature, because of its importance for resilience, because of its importance for competitiveness, and of course also because of its growing digitalization. And Europe is no exception, and a wealth of extremely passionate engineers, scientists, colleagues put their hearts and minds together to ensure that space contributes to our sustainable future. This is particularly true for Copernicus, and let me say perhaps a few words about Copernicus. All of you who are here, I think you know very well that Copernicus serves many EU policy priorities, from environment to agriculture, from marine to security, from defense to maritime policies, etc., etc. I think without a doubt, Copernicus is the world's leading environmental monitoring program and provides independent and authoritative information, crucial for the environment, for emergency and for security purposes. We have comprehensive data from satellites, so-called sentinels, and also so-called contributing missions, whereby we buy satellite data and imagery, and other observations that we use in order to provide the 6 thematic services of Copernicus. Copernicus clearly enables precise environmental assessments and informed political decision-making with millions of users in the EU and worldwide. And thanks to Copernicus, we are able to learn about our environment and also about, unfortunately, sad news like that, again, 2025 was one of the warmest years, that probably global warming limit of 1.5 degrees could be reached already by end of this decade, over a decade earlier than predicted. But it is important that we have this information. In the evolving environmental and geopolitical context, we are also facing other types of systemic risks, be it pandemics or biodiversity loss, but also supply chain disruptions, geopolitical conflicts, war-related matters. All of this plays now into Earth observation. So Copernicus is hence essential for Europe's resilience, offering tools for crisis management, preparedness, response. with real-time data about natural or man-made disasters, long-term monitoring of our climate, monitoring the state of our environment. But of course, we cannot stop there. And being good today doesn't mean we will be good tomorrow. Being the best today doesn't mean that we will be the best tomorrow. And this is why I would like to turn to today's subject matter. Artificial intelligence and broader digital transformation are key enablers to strengthen Europe's competitiveness and resilience. And Copernicus clearly is part and parcel of that. It's a foundational asset for the transformation by providing open and trusted geoinformation data and inputs for artificial intelligent agents, digital twins, and decision support systems. Embedding Copernicus big data into AI workflows can deliver benefits across literally all societal sectors: energy, agriculture, food security, health, transport, insurance, infrastructures, and so on and so on. Destination Earth is showing us a world of possibilities for breakthrough use cases based on big Earth observation data. Leading-edge modeling and AI. The value of AI and of digital twins for application areas as different as climate adaptation, extreme events, or border security is being demonstrated. And we want to leverage the Destination Earth high-precision digital twins fueled by Earth observations and advanced AI frontier models to enhance our Copernicus services. That's why I'm very happy that we're doing this workshop together with DG Connect today. In Copernicus, we have already started using AI models, but of course we need to improve and expand our product portfolio. And we also need to have access to supercomputing capabilities to sustain this. This transformation, I'm sure, will support Europe's leadership in trustworthy public interest, AI, technological sovereignty, and of course, in keeping Copernicus as the best Earth observation system in the world. Looking into the future, just to say that, of course, we have also embedded firmly Copernicus in the next European Competitiveness Fund, which will have a dedicated chapter on space and therein a dedicated chapter on Copernicus. Our primary objective is, of course, to continue and further develop Copernicus and making use as much as possible of AI-based services. We want to make the Copernicus services future-proof by embracing digital technologies and by enabling new exploitation paradigms by our users. Given the speed of developments in the field of AI, it's important that we also accelerate research and innovation. To bring more technologies to maturity in the midterm, we plan to update also our Earth observation strategic research and innovation agenda in close consultation with all relevant stakeholders. AI and other digital aspects will deserve a dedicated focus in this respect. Let me conclude by saying that Copernicus as Earth observation flagship program is the best of its kind, but we need to continue working on it, that it stays like that. We cannot miss the opportunity for the digital transformation and evolution of Copernicus. This workshop is very strategic and timely, and I would like to thank again all colleagues in DG Connect, in DG DEFIS, in HaDEA, who have made this event possible today. The large audience, I think, speaks for itself. Synergies between Copernicus and Destination Earth will be key to achieve our common objective. Together, they can revolutionize predictive analytics, operational preparedness, and strategic foresight for policy making. Thank you very much.
Thank you, Christoph, for these nice welcoming remarks. Let me now call to the stage Mr. Thomas Cordas, Deputy Director-General from DG Connect. So, Thomas, the floor is yours, and thank you again for joining us.
Thank you. Pleasure. Good morning to all of you. It's a real privilege to be here. To this very first event between Destination Earth and Copernicus, between Copernicus and Destination Earth. It's something that we have almost been dreaming for quite some time, Christophe and his management, and of course all our colleagues below us. And we are very, very happy that things start getting together, and we will get there little by little, but certainly with ambition and with a lot of will. So many thanks to Christophe for the nice words, and many thanks to all of you for being either in this room or online. The fact that we have the sheer volume of participants speaks volumes, of course. Artificial intelligence isn't just a headline grabber. It's a game changer, as Christophe has already said, and as many of you know, I mean, also when applied to climate change and to Earth observation. But let me take a step back and reflect a little bit on the larger context that is behind what we're trying to do. First of all, Europe's ambition is very, very clear concerning AI. We want to become the world's AI continent, as this was announced both by President von der Leyen, but also the European Vice President, Ms. Virkkunen. It's not just about setting global standards for trustworthy AI. It's about building the infrastructure, it's about innovation ecosystems, and it's about skills so that we can turn the AI into real-world solutions. The vision we have here for the AI Continent Plan is quite simple. First, build powerful sovereign AI infrastructure. Second, support AI innovation across sectors. Christophe mentioned a number of those, related very much to Copernicus, but there is much, much bigger picture, as you know perfectly well. So it starts from health and mobility, it goes to manufacturing, to energy, and then it comes to space and many other of these things. And third, we want to do it the European way, not just the way. You see all the discussion which is around now, Anthropic, OpenAI, and what's going on in the States. That's not the European values and the way to do it in Europe. That's something different that does not represent us. So our line to take and our way forward is extremely clear. To achieve these three ambitions that I mentioned before, three ways of building, Europe must act with ambition, speed, and certainly with a lot of decisiveness. That means that we need to scale up the infrastructure, we need to build these ecosystems I mentioned, and we need to connect all these infrastructures together with the talent we have, with data, with applications, and certainly with you, many of you, who come to represent startups, SMEs, and also industry. Now, at the heart of what we are building from an infrastructure perspective is the AI factories and the AI gigafactories. Probably, I don't know how many of you heard about AI factories. These are world-class compute infrastructures we are building now in 19 member states, 16 member states, 19 of those. They represent the best of supercomputers that exist in the world that we are building right now and for the next 2027 and for the next 1 year. So what's the idea? The idea is that we can somehow build the engine room for applied AI, where there is this abundance of compute capacity for AI training, for AI learning in general, for inference and fine-tuning, if you wish, and bring in actually the services and the expertise that you need so that you can all have access, fast-track access if possible, to all these infrastructures we are building from a European perspective. And our ambition is not just to build them, and many of them already exist, and probably some of you have already experienced access and the way to use these infrastructures for AI, but more broadly for simulation, modeling, and many other activities that you may have and applications you may have. So our idea is that all these should be interconnected. And we started interconnecting them through GEAN, through very high-speed networks, so that we can have a whole which is accessible from everywhere in the Union, and even beyond. This will ensure that if I am a young researcher in Athens, if I am a climate scientist in Helsinki, or if I am an SME in Lisbon, that we all can benefit from Europe's sophisticated AI compute infrastructure. So AI factories is one thing, which is more addressing the public sector, the researchers, the public sector, but also startups and innovative SMEs. For our industry, we're building something different. And this is the new initiative that our president announced February 2025, if I'm not wrong, yes, which is about AI gigafactories. So what are those? Why do we build those? Actually, they are with, I would say, at least one order of magnitude, if it's not more, in terms of compute infrastructure that our business and our industry can build. So build these kinds of gigafactories that can offer AI service like the ones I mentioned before to everybody. And of course, this is not going to be free of charge, because this is a business model that we have to develop together with our industry players and together with many financial investors, so that these gigafactories, and we hope to have to announce a few of them before the end of this year, and having started early 2027, the idea would be that we will have all the compute infrastructure and the services you need and business needs so to implement the Apply AI strategy that I mentioned before. So, crucially, everything will be open, open meaning not necessarily for free, but open meaning certainly that there will be abundant compute time in the next 2-3 years for everything that is ambitious, large scale, but also smaller scale applications and services, but also for entrepreneurs, for startups, for everybody to be able to innovate out there. This is how we want to create value in the global market. Now, where is Destination Earth in all this? You know that already, at least some of you know that Destination Earth has already used quite a lot of compute infrastructures that we have built in Europe with the 2 or 3 top-of-the-notch supercomputers that exist in Barcelona, in CNECT in Bologna, but also Lumi in Finland. Now, when we began to build this initiative, Destination Earth, back 4 or 5 years ago, even 6 years ago, we had in mind to be able to build something like the first digital twin of the Earth, which would be based on a more conventional model, meaning that we would use more modeling and simulation of data, using data that were abundantly available out there to be able to build this first model of the Earth and of the climate change. But ever since, things have been changing quite a lot. Ever since, we have AI. We have the AI revolution, or evolution for some, if you wish, and therefore we thought it would be extremely useful to be able now to couple not only the traditional methods, but also the new methods that AI is offering to be able to develop further the models of climate change and Earth modeling that we are building. And this is where we have really breakthroughs that these are, by using these kinds of methodologies, where we are coming with new operational reliability, with new accessible applications, and with trusted services for those who need them and to develop them. So this is a little bit Destination 1.0, Destination Earth 1.0. And we are moving very, very fast to its final implementation that we foresee will end in 2027, and then the new era will start as of 2028, as Christophe said. So what is this, what we built so far? First of all, we have unprecedented scale. The first digital twin of the Earth is running at a scale that we have never seen so far before. Second, we have street-level predictions. When an extreme event, for example, a hurricane, I hope there are not too many actually in the Mediterranean, although we've started seeing some of them with the climate change, or whether there is a flood somewhere, these are, and they threaten the region or in Europe, Destination Earth already provides some hyperlocal forecasts down even to 100 meters resolution that can be used directly for those who are dealing with disaster management, or for predicting that this will happen and therefore save lives and save properties to the extent possible. And then we have climate adaptation tools. They span from urban planning to heat wave resilience, and these digital twins of Destination Earth, let us really test, many of you have already tried, these what-if scenarios that are absolutely essential to be able to understand what's coming up, to develop early warning systems and better protect the lives of our citizens. So today, Destination Earth has the privilege of having, if I'm not wrong, around 6,000 users, and the number of users going fast up from one day to the other. So these users are scientists, public authorities, innovators, operational experts that are already engaging with Destination Earth on a daily basis. Member states are integrating also into their daily work the Destination Earth platform, improving weather forecasting, disaster risk management, and climate adaptation planning. And what's coming up then? So we are working now with the member states on future Destination Earth services and applications that are tailored to the needs and to the requirements that they have. So by 2028, normally a new version of the system should be fully operational with fundamental twin components for extreme events and climate change adaptation, which are prepared to onboard other twin components. So I told you about Earth modeling and climate change, Many other digital twins are under development right now. For example, those that are dealing with geophysical extremes, with biodiversity, with glaciers, and more broadly the modeling of the ocean heating, with agriculture. And all this is the planning to develop them and to integrate them sooner or later in the destination Earth and later on in Copernicus. Some of that is built under ESA, under the European Space Agency, and some other is built directly by ECMWF and the institutions with which we work quite closely together. Now, if we look further ahead, with Destination Earth 2.0, Europe will lead globally AI-powered climate foundation models. So imagine, for example, that we'll have generative climate models that are trained on data sets at resolutions that are at 5 kilometers or below, even 1 kilometer, so that we can simulate weather extremes with an unprecedented realism. We'll have, as I said to you, AI-enhanced twin agents. I compel everybody who would have good ideas about new engines and new digital twins to develop to come and see us, because we are looking for certainly many other good ideas that we can come and start implementing as of 2028 under the next MFF. And of course, we are looking also for new AI translation layers that would be turning the petabytes or the exabytes that we have of raw forecasts into insights that, for example, a city mayor or a civil protection team can actually use. So this is our ambition for the future, is really to make the Destination Earth the AI-ready engine driving Europe as a continent of climate intelligence, and as part of Europe's Apply AI strategy to deliver, therefore, this flagship action by developing and deploying an open-source AI Earth system frontier model. So with this, we would like to enable AI-driven applications and tools for climate resilience and at scale, to advance hyper-accurate weather forecasts, particularly for extreme events, and democratize access to high-resolution modeling. I think I've already mentioned a large part of this. And to give you a striking example, we have this forecast in a box demo in the room that was developed by the colleagues of ECMWF, our partner in Destination Earth, just next door. Go and look at it. So far, we were requiring somehow only supercomputers to be able to do these kinds of forecasts, and now you can see they run on a laptop and later on maybe even on our mobile phones. So this is how I would like to turn data into foresight and foresight into resilience. Let me spend the last few moments on Destination Earth and Copernicus. So today we stand really at a pivotal moment for Europe's digital and environmental ambition. So if we look further ahead, I already told you, and Christophe has already mentioned that we come together, DG CONNECT, DG DEFIS, to get the best of our teams, to get the best of our knowledge, to get the best of you, to work together, to be able to further develop Copernicus and Destination Earth for the years to come. So the convergence by 2028 is not just a technical issue. It is really a strategic and transformative step forward towards a smarter and more resilient continent. Copernicus has already transformed the way we observe our planet, and Destination Earth builds on this foundation. I think that together we can form a very powerful ecosystem for you, which is based on the model of observe, model, simulate, and decide. I think this partnership reflects a broader vision which is related to European cooperation at scale. And this is exactly the challenge we have right now in this very complicated world in which we are living right now. Shared data, shared infrastructure, and shared ambition can deliver global leadership in climate science and digital excellence. I think already Christophe has mentioned that we are developing a new innovation agenda under Copernicus and more broadly under the European Competitiveness Fund of the next MFF. So be tuned. I'm pretty sure that soon we'll come to you for consultation and for new ideas as the ones I mentioned before. So I think together we'll build now a unique European platform where artificial intelligence can transform the wealth of raw data into something which is actionable insights, unlocking new opportunities across climate services, agriculture, urban planning, energy, disaster resilience, and who knows what else. So this is a unique synergy that we are putting in place with the potential to catalyze a vibrant AI-driven ecosystem of startups and SMEs across Europe. And this is one fundamental issue that I would like to highlight. Copernicus and Destination Earth will be open to innovative services that definitely startups, SMEs, and many others can offer. And we look forward really how to make those even much more wealthy and much more convenient for all of you, so that also part of what we have in the ecosystem perspective can also thrive. Now, an ecosystem that's equipped to develop the groundbreaking cutting-edge AI products of tomorrow is exactly what we are looking for. So uniting Copernicus operational strengths with Destination Earth predictive intelligence, I think Europe will not just monitor change, but really will prepare for it. So our goal is clear: to summarize, leverage the cutting-edge technologies to support sustainable policymaking, tackle climate challenges, and ensure Europe's digital leadership. So I think the success of Destination Earth and Copernicus, and Destination Earth, will depend on one thing, which is above all, it's about you. So do not expect that the Commission will be the one that makes things happen. We will put the necessary layers and the necessary infrastructures and all the rest that I mentioned and Christophe mentioned, ecosystems, talent, etc. But the difference will come from you, from your ideas, from your perspectives, from your ambitions, from your, I would say, visionary ways of developing these things in Europe. And this is really the challenge that we would like to give here to you today. So you have the opportunity in the next 2 days to discuss, all of you, some of those. And really we encourage you to dive into the discussions, force connections with your peers, and take full advantage of our ambitious agenda. Together we can create enduring solutions that are the associated challenges, not just for our generation, but also for those to come. Many, many thanks, and I wish you a very stimulating workshop, all of us and all of you. Thank you.
Thank you very much again, Thomas, and also to the CONNECT team, also for pulling the workshop together with us. Thank you also, Christophe, and both of you, for setting the scene so nicely. We clearly have an opportunity in front of us if we pull AI and Earth observations together, as you nicely demonstrated. So it's now time for a short coffee break of about 30 minutes. So I invite you to also have a look at all the demonstrations. For those who are demonstrating, you can just plug your laptop in the HDMI cable, so it should be seamless to get yourself ready. This is the advantage of hybrid meetings for the people here on site, to enjoy also the presence of the colleagues. For those online, we'll reconvene at 10:30 sharp, please, for the session 2. Thank you again. Okay, welcome back. I hope you enjoyed the demonstrations and the coffee and the drinks. I will also invite you during lunch break to visit the demonstrations. Some of them are really impressive. So there is an entire new world opening, and so it's good to witness and see that. So let's now move to session 2. I will invite Mauro Facchini, my head of unit, to chair that session. I will be monitoring also the Slido for questions online. So Mauro, to you.
Yes, so good morning everyone. It's a great pleasure to have you here in presence and online. Repeating what was already said this morning, it has been a challenge to organize this event. I think, unfortunately, the strikes have prevented some people to come, but considering the registered numbers here in Brussels and online, I think it's the biggest workshop we ever had. So I would like really to thank personally my Mitch, that you have seen before, because he was really behind the organization of that, and the whole team that supported, communication team and so on, with DigiConnect and with HaDEA, because I think if we are here and if it works, it's also thanks to their commitment. So I'm Mauro Facchini, I'm working at DEFIS. I'm in charge of Earth observation and as such also of Copernicus. I have the pleasure to moderate this session about artificial intelligence and machine learning revolution. We will have 4 speeches in the beginning, and then there will be a panel with 2 colleagues that I will also moderate. So the 4 speeches are coming from DG CONNECT, but also from entities with whom we usually work in the frame of Copernicus and Destination Earth. So it's from ECMWF, it's from ESA, and from Mercator. While the panel will be with representatives of national member states, so there will be a representative from France and a representative from Italy. I propose that we start immediately because I'm very tempted by the chocolate, so if we want to make it by the time, I think we have to finish on time. And so the first speaker is coming from DG CONNECT, so it's my colleague Gaspard Demure, who is Deputy Head of Unit Artificial Intelligence, Innovation and Policy Coordination from the EU Artificial Intelligence Office in DG CONNECT. So Gaspard, the floor is yours.
So good morning, colleagues, and many thanks for the great opportunity for the invitation. It's really an honor to be able to speak with the Copernicus and Destination Earth communities. So I'm coming from the AI office in DG CONNECT in the European Commission, where we are trying to coordinate the AI policy at the EU level. I will echo, of course, the elements that were mentioned in the introduction by our Deputy Director-General, Thomas, and try to explain to you what's there for you, for your community, for your companies in developing the next steps in the AI policy. As was mentioned in the introduction, Europe now has a very clear ambition on the AI policy. We want to be a leading AI continent, and that's what we have explained and detailed this year, in 2025, when publishing in April the AI Continent Action Plan. 5 key domains, to reach this very ambitious goal. Infrastructure, data, skills. We also want, at the 4th point, to really go into the sectorial dimension of AI. I'll go back to this. We have a great strength in the European Union, which is to be able to use the data from the specific sectors, such as the space sector, to specialize the AI models. So not working just on the large language model, but also to fine-tune the model for the specific needs of a sector, and we'll go back to that. Final point, we also want to simplify the regulatory environment, and we've been publishing recently the Digital Omnibus, explaining more precisely how to apply the AI Act. But let's dig a bit into these 5 dimensions to really explain what exists already, what type of tools you can actually use. So our DDG was mentioning the large infrastructure for the development of the last generation of AI models. We are speaking about AI factories, the 19 AI factories that are in the making, selected and in development. We are also speaking tomorrow about the gigafactories. The concept here is really to have very high level of computing power to train, infer, and deploy the latest generation of AI models. We are not starting from scratch, and I know that you will have further discussion with the colleagues from Connect C1 on that more precisely, but we have a network of high-performance computing in Europe. We are adding to this existing computer an architecture and a number of GPUs that are dedicated to the training of AI models, so that we can, in Europe, actually develop and deploy the latest generation of models, including in the field of space and defense. For the AI factories, we're speaking about up to 25,000 GPUs, so this is already quite a lot. This is very efficient, and this is already available in many of the European countries. Now, when we are speaking about the gigafactories, we will go a step further. We are speaking up to 100,000 GPUs, so this is to equip Europe with the type of infrastructure that are used in the rest of the world for training the most advanced AI models. So that's very important. And of course, you know, the concept is to give access to this infrastructure so that the specialists in a dedicated sector are able to use that computing for the development of the AI models. Now, this is for the pure computing power, but when we are speaking about infrastructure, we are not speaking just about HPC and computing power. We are also speaking about cloud, and this is very important also for your different stakeholders to be able to use the flexibility and also the inference capacity of the cloud. You know that in the AI Continent Action Plan, we have announced the Cloud and AI Development Act. This will be adopted very soon as part of the tech sovereignty package. There, the ambition is very high. We want to triple the number of data centers in Europe in the next 5 to 7 years. And we are working a lot on everything related to permitting, but also to the sustainability dimension of the data centers. So what we want to do with infrastructure is really to provide with a continuum of tools so that we can train, develop, infer, deploy the models made in Europe, developed by AI developers in Europe, and made available to the community that can deploy or use it. It's not just about, you know, developing the models, it's also matching offer and demand so that we can really create a community which is taking benefit of the development of these models. So that's for the infrastructure. Second point, data. And I was listening to the introduction. I mean, of course, in different sectors in Europe, we have enormous amount of high quality data. This is the case in your community, also thanks to the work from Copernicus and DestinE Earth. What we want to do is really to go the next steps and to use these data to increase the quality of the model that are trained with this data. This is why we have adopted at the same time as the digital omnibus our data strategy at the European level. And there, I mean, the concept is quite simple. We want to increase the volume of available data, but also the quality, sanitization of data. And we want to offer safe spaces for the different stakeholders to be able to share the data so that we can improve the quality of the final model. This is the concept of the data labs that will be deployed, including in the framework of the AI factory, providing a safe space for the management of the data. Now, I want to insist on a third point, which is extremely important for the community, which is skills enhancement. And there again, I mean, we are at your disposal to provide the tools that are already existing. So we've seen when discussing with the companies that a great challenge is the overall AI literacy of the workforce. This is a problem in all sectors, and this is also a challenge in the space sector. What we are proposing here is a coordinated action at EU level. We call it the EU AI Academy, Skills Academy. We will be working very closely with the member states to increase the number of initial training in AI, so PhDs, masters, by also harmonizing or working together on the needed skills for this initial training. We will also use the EU programs for increasing the exchange between the member states on this initial training. But we will not stay only at the master's PhD level. We want to work also in reskilling or upskilling the workforce in the companies. We have, for that, a very important tool, which is the European Digital Innovation Hubs. I'll come back to this later on, but we have a very important network of more than 200 of these hubs existing in all member states, but also in associated countries, in Ukraine, for instance, or in the EEA countries. These hubs are very close to the companies and to the local authorities to provide training on AI, how to use AI, how to increase the literacy in the company, how to implement the AI Act. So this is not a kind of top-down approach. These are really hubs that are locally based and that are providing training on specific elements of AI and digitalization to the companies and to the local public administration. Now, A fourth element, which is extremely important, is the sectorial dimension to the development of AI. So we were speaking in the beginning about, having the most advanced AI models, large language models, general purpose AI models, but we also have a very great strength in Europe, which is the leading companies in a number of sectors, including in space and defense. This is coming directly from the Draghi report, this idea that we should build on the strengths coming from our sectors. And we have very recently, in October last year, adopted what we call the Apply AI strategy. And the Apply AI strategy is really this deployment of AI in the sectors. We have identified 10 verticals where we want really to work more precisely on the fine-tuning of the models, the training of the models for the sectors. It goes from automotive to energy, and we have a dedicated verticals on space, security and defense. We have there a number of actions that we are proposing. One of these actions is the deployment of highly secure infrastructure for the training and deployment of dedicated AI models for the space sector. So this is something we want to work with the community. For that, we have developed a governance structure, because of course we are not going to decide from Brussels what these models will be and what are the needs of the community in terms of the deployment and development of AI models. The Apply AI Alliance is this structure, this governance structure, where we want to engage with you on the long term. We will have thematic working groups and thematic workshops. We have started to develop them, and this webinar is really important from that point of view. We want to really understand your needs for the development of the specific frontier AI models, and we want to do that on the long term to see how we can fine-tune the models to the specific need of your industry. We are also working in the Apply AI strategy in the context of cybersecurity. We know it's critical to your sector, so we will continue to do that, to use AI as a tool for developing cybersecurity assessment and mitigation measures. I will stop with the last part, which is the simplification of our regulatory environment. You are all involved in that, implementation of a safe AI. This is important, of course, for in-orbit, but also on-the-ground infrastructure in the field of space. We are working there very closely with the stakeholders to explain, the different pieces of legislation. We have simplified, we have made a proposal for the simplification of the reporting obligation for the AI Act, but we are there also at your disposal through the network of European Digital Innovation Hubs to explain, concretely how this would apply to your business cases. We have developed very recently an AI Act service desk, which is there to listen to your question and to provide legal certainty. I will stop with a final tool, which is of really importance for you. Very important, once we have the models, once we have the data, to test the prototypes, the system, before we are actually putting them in production or on the market. We have 4 testing and experimentation facilities in Europe in different sectors: agri-food, urban planning, health, but also manufacturing and robotics. And these testing and experimentation facilities bring the different elements together. We need to work as an ecosystem with the AI factories, tomorrow the gigafactories, the European Digital Innovation Hubs, and these testing facilities to really understand how the models work and how we can put them on the market before we actually deploy them. So, in a nutshell, we have a lot of tools that are already at your disposal. We are there to discuss with you on the long term, to understand the needs from your specific community, and to create the frontier AI models of tomorrow for being the most competitive actors in Europe and globally. I stop there. Many thanks for your attention.
Thank you very much, Gaspard, for introducing to us the European Artificial Intelligence Strategy, and where actually we are we are going. And then let's now enter into three presentations that are mostly on the use of artificial intelligence. And the first one will be a keynote by Matthew Chantry, who is strategic lead for machine learning in ECMWF. So he will give us a keynote on modeling and monitoring the Earth systems, the artificial intelligence revolution. Please, Matthew.
Thank you so much for the introduction, and it's a pleasure to be here. We've heard already several times what a wonderful opportunity this is to bring together different groups to really embrace and take advantage of these opportunities in AI. So the thing you'll be hearing me say the most over the next few minutes is next slide, please, which you'll be hearing me say first now. So just a quick background on who are we, ECMWF. This is the European Centre for Medium Range Weather Forecasts. So we just celebrated our 50th anniversary last year, and our mission is to deliver global numerical weather predictions, focusing on the medium range, so that's over the first 2 weeks, but not just on that, and also with capabilities for monitoring the Earth system, particularly in connection with Copernicus. And this is very much done to and then with our member states that are 30 countries across Europe. So we're based across 3 sites with over 500 staff, and I guess what we seek to do is bring together 2 parts. So we run operational services delivering very timely weather and climate forecast data, but we also aim to be on the cutting edge of research, sort of pushing the boundary of how we can do numerical weather prediction, climate monitoring, etc. Next slide, please. So we are honoured to be the implementers of the Copernicus Climate Change Service, which aims to provide authoritative information about the past, present and future climate in the world, in Europe and the rest of the world. And on the next slide, please. They also play a similar role in CAMS, so the Copernicus Atmospheric Monitoring Service, which is about providing consistent, quality-controlled information related to air quality, health, solar, greenhouse gases, and climate forcing sort of across the world. The next slide, please. And then sort of the third of this trio is be implementers alongside ESA and EUMETSAT in Destination Earth, which we heard already about, where we're looking to build digital twins of the Earth system, to sort of bring the next frontier, bring HPC and modelling together to push the boundaries of what can happen in weather and climate. So that's the context of who we are, what role we're honoured to play. Now on to the topic of AI or machine learning. So you don't hear very much about it, and the reason is it's not particularly very useful, the whole theory of machine learning. We hear about it a lot as an experimental science, which is honestly far more what it is, but there is some theory of machine learning. It says if you have a neural network and you make it sort of big enough, you have enough compute, you have enough data, any relationship can be learned. But what that doesn't really tell you is sort of when that's true. So if we go on to the next transition, it doesn't tell you the sort of answer of, for a given problem, whether you'll get to that. And so this is where the experimentation comes in, but you know the 2 ingredients. It's a bit like a sort of recipe. You know that if you have enough compute, you have enough data, you can do this. And so you're looking to find an opportunity that brings those 2 together. So next slide, please. So we're first going to start through the lens of weather and then move along to other places, because that's where, from our perspective, the AI revolution sort of began. So there was already a revolution, we would argue, in place that's been happening very quietly and slowly over many decades. So here I'm showing the plot of how accurate weather forecasts are by one measure of skill. So you're looking for the higher, the better, at various different timescales. So looking at day 3, day 5, day 7, day 10, from over many decades. And sort of, you can see a few different trends in that, but the main one I want you to come out with is that this has been steadily increasing over time. You might not see it day to day in your weather forecasting apps, but slowly but surely, weather forecasts have been getting more accurate. And that's been through a range of things. That's been through sort of improvement in physical modeling, better use of HPC, that's bringing these together. And then over the last couple of years, there's been a new entry to this space. So if we go to the next. So we now see some new lines come on top. So the physics models have continued to get slightly better, but a step above at each of those timescales is AI-based models. So these are models that are trained on physics-based data, which I'm going to show you in a second, but that despite using physics-based data, they're able to produce predictions that are more accurate. And so this is a very exciting opportunity when you see that broadly these models have achieved in a couple of years what's the sort of progress that would take about a decade of development in physical models to get there. Next slide, please. So, how has this happened? This has happened through a range of different actors, some of them already in the field of weather forecasting, and a lot of them actually coming from outside, seeing that we have this nice combination there at the moment, seeing that we are in this sweet spot of data and compute to allow us to build these new models. And so this has happened from the sort of start of 2022 over to present, where models have been getting bigger, better at doing a range of different weather forecasting tasks, and provide us with these opportunities. They've very much been focused on writing an academic paper, right? Getting into nature is the goal of these works and not turning it into operational services, turning it into end results. And that's what we sort of pride ourselves at ECMWF in being particularly good at. Next slide, please. So we already heard about the accuracy things. Perhaps even more exciting than accuracy is what these AI-based systems can do in the weather and climate space from a compute perspective. So we run 4 times a day weather forecasts out to 15 days, and those take about 50 nodes on our supercomputer and about an hour to go away and make that prediction, which is a considerable amount of energy to go away and make that prediction. So these AI-based forecasting systems are capable of running in just, say, 2 minutes on a single GPU and producing this accuracy. So this opens up a whole host of possibilities. This can open up larger ensembles for a better estimation of uncertainty. It can open up a more democratization for who can run these things, or just more rapid forecasts, so more rapid updates, getting a forecaster earlier information on when an important decision can be made. Next slide, please. So an example of this, the beauty and also curse of weather forecasts is they're used for so many different applications, so we can say more skillful, what does that mean across lots of different things? Well, I think tropical cyclones are really a clear one where the advantage can be played out really clearly. So here we're showing an example of an event where we have the observed track in black, we have the physics-based model in blue, and we have the red model, which is the machine learning forecasting system, our AIFS, in red. And you can see at this initialization time, the model does a far better job of tracking the true track. This is something that for the physics-based model, it locked onto about 12 hours later in real time. So in this scenario, it's quite representative for a setting where machine learning models are perhaps capable of giving you 12-hour earlier information on when to make an important decision. And this is sort of carried out across lots of different application areas, but I think tropical cyclones are perhaps the ones that most clearly sell this story. Next slide, please. So how has this happened, right? We know that the recipe is this combination of compute and data, so why are we in this space, in this setting of weather forecasting? The next slide, please. So for data, on the next slide, we're going to see, thank you. Next slide, please. The foundation of this revolution, all of those papers that I listed above are citing the same single paper, the paper that describes the implementation of ERA 5, which was produced and maintained by ECMWF as part of the Copernicus Climate Change Service. So this is a data set that brings together observation data through the lens of a model over the last six decades to provide a consistent view of the Earth system every hour, every place on the globe. So this makes it a sort of a gold standard of machine learning data sets, and both the skill and accuracy of this, but also the ease at which it could be retrieved and used is one of the big reasons why we saw lots of people building on this, the fact that it wasn't just one person making a paper on this, but lots of different papers that seek to build on top of this. Next slide, please. Because in fact, sort of ERA 5 is one example of this, but in fact, I think Europe can be very proud of producing a whole range of exciting data sets that are really leveraged for this AI revolution. So an example I'm not showing could be the data sets we're building within the Copernicus Atmospheric Monitoring Service, where we have similar reanalysis, these observations through a lens of a model. But I'm also showing here simulations from the digital twins of Destination Earth, where we're showing climate forecasts delivered on EuroHPC, specifically LUMI, at kilometre scale resolution over decades of forecasting capabilities. So these are really special data sets that can really enable us to build these AI-based systems. Next slide, please. So we know about the data. What about the compute? If we go on to the next slide. So the power here is the wonderful opportunity that is the EuroHPC. We've heard about this already several times, but I think it really does need stressing. If it doesn't appear in every talk, we're missing a trick, because this is really the opportunity that we have here in Europe. Here I'm talking about EuroHPC, but there should also be flags talking about the AI factories and AI gigafactories, that we are in a special place in Europe to take advantage of this data and bring it into building sort of state-of-the-art machine learning models. So next slide, please. So, and if we slip again one step further, you can tell I was planning to have a clicker for this to go through with fewer next slides, please. You can see that in the time period of this happening, this revolution, if we go to the next slide, ECMWF, we saw this coming, and we're very keen to take advantage of this. We saw this as an opportunity to improve our product portfolio, deliver more exciting or sort of more impactful forecasts for our users across Europe and beyond. And so we developed, starting in 2023, and then implemented last year in operations, 2 different forecasting systems. So if we go on to the next slide. We delivered 2 forecasting systems, both called the AIFS. So this is in homage to our physics-based system that's called the IFS. So this is Artificial Intelligence Forecasting System. We developed capabilities that are capable of forecasting a single deterministic, sort of best estimate of what the weather forecast will be, but also a probabilistic estimate via a series of different ensemble members that can give us reliable uncertainty information about where our weather is going to be over the coming days and months to come. And these were implemented last year. Next slide, please. So how do these compete? Well, the beautiful thing about weather forecasting is how many different things we're producing. And so I can't easily give you that sort of summarized in a way that's easily explainable. But I can give you a snapshot through one field. So here, if we look at surface temperature accuracy, so here we're looking at accuracy over time evolve as we struggle with a chaotic system. And we're looking for things that are lower to be more accurate. We can see that the AIFS is outperforming the IFS, the physics-based model, but also we can be quite pleased of our comparison compared to big technology companies. So here I'm showing one of Google's models. They were featuring in that space above, developing some of these models, doing a very good job of getting lots of the headlines, the Nature papers, but we can actually see that for quite a few fields, our machine learning-based systems are even outperforming the state-of-the-art produced by big tech and others. Next slide, please. So an example of this, beyond sort of tropical cyclones, we can see that extreme temperature predictions are also something that these models are doing a very good job at. So here I'm showing an early heat wave in April 2025. So for the season, outrageously warm temperatures. So on the left, you have a series of observations. In the middle, you have an example forecast from a physics-based model. And on the right, you have the forecast from our probabilistic AIFS system. And we can see, just basically looking at, for the darker reds, the more extreme temperatures, that this model was doing a better job of predicting these unseasonably warm features. And this is interesting for the question of sort of forecasting in a changing climate. I believe temperatures this warm had never been seen this early in the year. And so this is a demonstration that these forecasting systems are capable of producing sort of novel events, which are obviously key to making sort of reliable predictions of extremes in our changing climate. Next slide, please. So how have we gone away and done this? Sort of what has been key to this? So we've been building in collaboration with a lot of our member states across Europe, national meteorological and hydrometeorological services, a framework for building data-driven weather forecasting models and data-driven climate forecasting models. This is called Anemoy. This is an open source ecosystem, so anyone can download and use it. And it aims to produce a sort of end-to-end ecosystem that goes from data curation all the way to operational inference. So this is about sort of being able to interface with Europe's climate data stores and other data repositories to build training data sets. So if you want to if you want to train at scale, for example, on Euro HPC, you can't just build a generic data set. You need to be thinking about what the application is you want to run on. So then we build some really HPC-capable machine learning models, things that can scale to the wonderful ecosystem that is Euro HPC, AI factories, AI gigafactories, and then an inference system that can give you reliable predictions in an operational context. And so this, for us, was a key development to allow us to then build on this, which is now what I'm going to go and talk about over the next few minutes. Next slide, please. So Anemoy is serving a range of different applications. So this is sort of global weather forecasting, where you can go to quite high resolution over the globe, leveraging some of the some data sets like Copernicus, Destination Earth data sets. It's about doing regional sub-kilometer scale forecasting, as we see in the middle, and then also directly using observations within that framework to be able to leverage Europe's state-of-the-art Earth observation capabilities. Next slide, please. So that's the setting that brings us to this point. So this is what we've been doing within our role as an operational weather forecasting centre on behalf of our member states. So now I want to talk about how we're building on this to deliver across Destination Earth and Copernicus. Next slide, please. So within Destination Earth, what we're looking to do is expand the sort of atmospheric forecasting capabilities that were been built in the AIFS to build a sort of foundational Earth system representation across the different components of the Earth system. So this is about building modeling capabilities for ocean and sea ice forecasting and modeling, land evolution, waves, and hydrology. And here I'm showing some videos of the evolution of the AI-based systems that we've been delivering. So here we're showing the evolution of sea ice in the Arctic, where you can see that the observed sea ice edge is in this red line, if that's clear enough for you there. And also showing the evolution of soil moisture over Europe on the right to show the evolution of land surface dynamics that are well captured by these forecasting capabilities. So these are, again, looking to continue the trend that we saw in the atmosphere, so leveraging the data sets that we're building in Europe, leveraging Euro HPC capabilities to deliver systems that are more accurate and also are capable of running in a matter of minutes on a single GPU. Next slide, please. So, beyond the models themselves, actually, we heard already about the forecast in a box concept, which my colleague Tiago was demonstrating outside. This is trying to take this portability, this fact that you can run on a single GPU to the next level and really build into this democratization component. So this is about building a software ecosystem that can run on the cloud, it can run on Euro HPC, it can run on your own hardware, where it is preparing the initial condition data to run a model, it's running a model, and it's allowing you to customize the products that you want to go and create and visualize. So taking advantage of the fact that these models are far more portable than their physics-based counterparts to allow you to go and interact with them yourself. And so if you want to learn more, go and see my colleague Tiago, who's outside in the breaks, demonstrating how this can in fact run in a matter of minutes on a box that he's brought live to this venue. Next slide, please. And so, yeah, so this is a capability to run on various systems and also to choose from a flavor of models. So this is where we're going to be building in these Earth system component models developed within Destination Earth to allow you to pick and choose which parts of the Earth system you want to go away and model for your specific user application. Next slide, please. So it wouldn't be an event on AI without talking about large language models. And here we have another opportunity to interface the wonderful data that we're constructing within these programs, within Copernicus, within Destination Earth, and where we're developing within Destination Earth and also within the context of the Copernicus Climate Change Service, digital twins to allow a wider range of people to directly interact with our data. So I'm showing a prototype of something that would allow you to generate sort of a human request. So I would like to know what the temperature will be like in Italy in 50 years' time. And the way you can build trust in that is that's not only going to go and give you an answer, but it's going to show you how it went to the data stores to go and get that data. So you're going to be able to trust why that made the right thing. It's not hallucinated a random number for the year 2050. It's said, actually, I know this is the case because I've gone to this data source, I've gone to probe what it says, and then I've delivered that answer to you. And that's meaning that you can then perturb that. You can then say, well, actually, I'm also interested in what's happening in Greece or beyond, and you can adapt that request to go away and sort of interact more directly with the data. So it's not only giving you the answer, it's also teaching you how to interact with these data stores. And we're also looking to build similar capabilities within C3S as well. Next slide, please. So what's happening in other parts of these activities that we're responsible for. So here we're looking at, the previous slide, please. You're too fast for me for once. So here we're starting with the Copernicus atmospheric monitoring system. So here we have, again, a wonderful data set to work on. So within the CAMS program, we've been building reanalyses data sets, which are these observations through a lens of a model that provide, again, a great data training source to build these systems. And we've been demonstrating this by extending and building an AIFS system for atmospheric composition. So here you're seeing a video on the bottom left showing the evolution of total aerosol optical depth. And then on the top right, we're showing the evolution of the ozone hole over time. And actually, the one on the right really demonstrates the twin possibilities of AI in one place. Because here we're showing the true value of the ozone hole as measured by observations, the forecasting capabilities delivered by the physics-based model at day 5, and then also the forecasting capabilities of the system, the machine learning model at day 10. And we're able to run out to day 10 because the models are cheaper, and so we can run out more easily without using the same level of HPC, but also the enhanced accuracy means there's a better reason to go out in that distance. And so you can see in this scenario, we're able to deliver an interesting capability with this prototype that we want to look to explore and further develop within the next stages of the Copernicus program. And again, the whole prospect of why this was able to be done is based on leveraging the data of CAMS, the compute, for example, of your HPC, and also then the infrastructure, such as this is adapting Anemoy to these capabilities. Next slide, please. So an example of something that's happening similarly within C3S, or the Copernicus Climate Change Service, is about leveraging Codex, so regional climate data. Back, please. Can we go back one slide, please? Yeah, perfect, thank you. To deliver sort of enhanced regional uncertainty quantification. So this is about using tools like machine learning downscaling to connect up all the excellent sort of regional climate simulations that have been run for some scenarios, but not necessarily all, with archives like CMIP to bring these two data sets together, to use machine learning to learn the interrelationship to those, to bring really high-resolution climate information into the Copernicus Climate Change Service. So this is a work that's just starting, and I'm sure you'll be hearing more about this over the coming years. Next slide, please. So I've talked about the modeling capabilities, but how can we go about trusting these things? So you might hear the term black box in a lot of settings. How can we trust our ability to use AI in an operational setting, be that for weather forecasting, monitoring of our climate, of our atmospheric composition? So I think there are broadly 3 pillars that are really useful to have a good understanding of, to do really well, to enable us to build that trust, to start using those. So the first is robust uncertainty quantification. So this is not just about building a single prediction, but building, say, an ensemble or a reliable probability distribution that you can assess in a way to ensure that when a model gives you a good prediction, you have an understanding of the uncertainty about that. The second pillar, next slide, please, is about extensive verification, right? So we are, this can be about running large numbers of simulations in a historical period, independent from the training period, to give us robust statistics on how accurate these models are, so we can trust their generalization capabilities. An example of this is either our scorecard capabilities, which we use for evaluating our weather forecasting systems, but we're also trying to do some of these things in a public setting to build trust through the community. So an example of this is the AI Weather Quest, which is being done partly with DestinE Earth and the World Meteorological Organization, which is to seek to understand the capabilities of machine learning for forecasting over the next few months, and where we bring out into a competition, an opportunity for intercomparison of different modeling capabilities. And then the final pillar, next slide, is explainability. So I'm sorry this slide isn't resolving as well as I'd hope. So trying to really probe the black box and understand that these models behave in the same way as our physical systems. So looking at the interrelationship between variables over time to understand that they've captured the physical capabilities. Next slide, please. And next slide, please. So, where are we going to go? How long do I have? 5 minutes, perfect. So, what's next for this future? So, ERA 5 is not what's next. ERA 5 is what's been really powering the last few years of change, but it does point us to where we're going to go next. Next slide, please. So ERA 5 was started in 2016 based on the state-of-the-art for physics models in that time. And in that time, as you can see, if I go back to this evolution of how accurate physics models have gone, you can see that as I move that line across, a decade of investment into physics models is still a very noticeable impact. These models have gotten precisely more impact, have gotten noticeably more skillful. And we're seeking to build on that with the production of ERA 6, which is about to enter production, which will sort of leverage this decade of investment of physics models into the next generation of this reanalysis. Next slide, please. So this is going to deliver enhanced reanalysis products. So this will be increased resolution. For example, it will do a better job of capturing the intensity of tropical cyclones, and is really a very exciting opportunity to again push these models one step further in their accuracy capabilities by leveraging this decade of investment in physics-based models. Next slide, please. Another component of what we're looking forward to and exciting to do is this work in strengthening early warning in Africa, and particularly this ARCS, so African Regional Centres of Excellence. So this opportunity to build on the developments we've seen in AI modelling capabilities, to work with African partners to leverage these capabilities there. So here the opportunity to increase forecasting capabilities is even larger because the compute limitations are even more felt there, and so the opportunities to deliver from 50 nodes down to 1 GPU, from 1 hour down to 2 minutes, really can be a game changer in this space. So this is work that's about to start where we work is Europe and Africa in partnership through training, through tools, through data exchange to build the next generation of forecasting systems for Africa. Next slide, please. So, back to the start. The theory of machine learning says that given enough compute and data, any relationship can be learned. So hopefully what I've shown to you really is that we are in a special place in Europe here. We have built ourselves a thriving ecosystem. This is not talking about ECMWF, this is talking about Europe as a whole, where we have built the ecosystems for compute through things like EuroHPC, AI factories, AI gigafactories, and then also these data sources, so Copernicus, DestinE Earth, and other data programs that are delivering these state-of-the-art opportunities in data. And so next slide, please. So I think Europe, I believe, can continue to lead in this space. Next slide, please. And it's going to be achieved by continuing the great investments we've done so far. So continued investment in compute. We heard about AI gigafactories. Continued investment in physics-based systems. It can be tempting to say that we need to only invest in AI, but hopefully the message you've heard today is that this is going to be achieved by the leveraging of observation data through the lens of physics-based systems. Physics is doing a great job of in-painting between these observations, and obviously investment in AI. And in concert, these can enable us to have a leadership position in this space. So with that, thank you very much, and I look forward to questions.
Thank you very much for this enlightening presentation. I will leave maybe the place for a couple of questions. I don't know if there is one question from the floor, if there is anything online. We start with the one online. I understand, Mitch, there is one. You want my mic?
Should be working?
No.
No? Yeah, so there are a few questions online already. So a question directly to Matt. Will knowledge get lost if potentially only AI models will be used in the future compared to mainly physics-based models where humans are aware of the relations and mechanisms? AI black box as another buzzword here. And there was another question, will we, shut down the numerical models? There were a few questions along those lines as well.
Well, so hopefully my end of my last slide has somewhat answered this question. This is not really seeing this as something that's replacing physics-based capabilities. It's really building on this. So that we have to continue to invest in this because our observation network is wonderful. We can do a lot with observations alone, but there are gaps in our observing network, and we can use physics models to fill in between that space. And so we need to continue across the investment of physics models. These are still going to run in operations. It's just a new tool that we can use that has enhanced interactivity.
Thank you. One question from the floor. I have one. Oh, yes, please. This is an in-house question.
Yeah.
Actually, it's not a question. It's just a comment because you've been very cautious and rightly so on ERA 6, and I just wanted to put the record straight because as of Friday afternoon, ERA 6 has started running, so it's now official. ERA 6 is in the making.
There we go. Thank you, Carlo.
No, I have a question myself. I mean, when we have compared the weather simulations between, let's say, the traditional high-performance computing and artificial intelligence, you mentioned accuracy on one side and timeliness. As a manager, my interest was, what about cost? Is it cheaper to do with artificial intelligence, or the price would be similar?
It's a good question. Possibly not with a very good answer, because I think there are lots of different lenses to view that through. So if we only look at what's happening now, if we look at sort of a few hours ago, an operational simulation happened for both physics-based models and machine learning models at ECMWF in Bologna, and one of them took perhaps as little as 10,000 more, or as much as 10,000 times more energy to make that prediction. So the physics-based model took 10,000 times more energy to make that prediction. And even though GPUs are currently slightly more expensive than we would probably like, that would still be delivered at a sort of lower cost. The reason why it can get a bit more complicated is deciding sort of the investment that's got you to that perspective, right? So you've had to train lots of models to build those systems, but you've also had to do lots of physics experiments to give them. So the real answer is a bit murky. We believe still the machine learning models are a lot cheaper, but given that they also leverage these physical model developments, the costs cannot really be separated entirely.
Thank you. Thank you very much. So I propose that we move to the next speaker. Thank you. Another round of applause. Thank you very much. Yes. So actually now we move to a European Space Agency presentation. It's Luca Girardo. It will be about the artificial intelligence revolution in Earth observation data processing. We will try with a clicker if it will work. So can we put on the presentation and then we can test the clicker?
Okay.
Okay, 1 second, and we can start. And while we wait, good morning. I'm Luca Girardo from European Space Agency. And in the next minutes, I will show example how AI is enabling the move from raw Earth observation data to services that people can use for actionable insights. In short, from Earth observation to Earth conversation. And now we test the clicker. Is not any results. So, no.
No, we continue the traditional way.
Okay, so next, please. Okay, next, please. And next, please. So let's start from the data reality. Today, Earth observation is in a golden age. First, volume. We have an unprecedented amount of Earth observation. The Sentinels are producing more than 3.2 terabits of data per day. We have more than 85 petabytes of data in our archives of Sentinel data alone. That is equivalent of rough 3,500 years of streaming of HD videos. But then we have velocity. New missions are coming, and data refresh is faster. Just with the Copernicus expansion missions, we expect 6 times today daily production. And the third element is variety. So we have many sensors, many resolutions, many domains. So land, ocean, atmosphere, everything together. But this also creates complexity. Data is fragmented. Legacy formats are different. We have heterogeneous interfaces, clearly by passing of time. It is hard to combine all this information in one consistent view, and it's costly to exploit at a scale. At the same time, this is a big opportunity. If we analyze data in a more holistic way, we can transform this in actionable intelligence, not only maps and files, but information that people can use. And there is another opportunity for Earth observation AI, how we represent the Earth. For many years, we forced Earth's data into planar grids. Now, together with our colleagues at ECMWF, we are evolving towards spherical representation, for example, hill peaks. This supports truly global analysis without treating the planet as a flat image. So the challenge is clear. Abstract, simplify, and democratize access, so that Earth observation data is not only for Earth observation and climate experts, but also for policy, industry, and academia. And this is exactly where AI starts enabling the transition. Next, please. Before presenting example of service deployed using AI, one quick word on DestinE platform on which these services are deployed upon. The DestinE platform is a flexible ecosystem of services. You can discover DestinE data and exploit them locally. It offers a catalog of applications and AI frameworks as a service. It builds continuity with Copernicus and provides scalable services for industry. I will use 2 examples out of that services. First, GeoAI, then data storytelling with AI assistance. For the people here, you will be also able to have, let's say, a talk with operators, and you will be able to see the services there. But for the people online, you just go on the DestinE platform, you log in, so if you didn't register till now, now is the moment, and you can start using that services. Next, please. Let's start with the GeoAI and DestinE. The key point is flexibility. You can train an AI model for your specific Earth observation use case, for example, detection or segmentation, and apply it to similar objects. GeoAI is built for Earth observation diversity, different resolution, image type, and sensors. And it is accessible. It is no code, so you don't need to be any AI or geospatial expert. It is built on DestinE data, including climate adaptation digital twin datasets, and Copernicus Sentinel-2 Level 2A. And it is operated by FlyPix AI. Next, please. So, understanding changes on Earth is hard. In many cases today, it still means manual work and specialist skills. And here, GeoAI is designed to reduce this barrier. Next, please. Now if you go back, sorry, one slide, we missed probably something. Back one. And if you just do a click, okay. Well, here should be a video of GeoAI. So I will just explain in words then. So GeoAI is designed to reduce this barrier. You show a few examples, and then the system learns how a model for that use case. So here you would have a forest example. You will see here in the demonstrator also when you come to our demo booth. Instead of tracing everything by hand, you provide a notation, a few representative areas, and then the system trains a model. This can be detection or segmentation, depending on the task. The goal is to learn what forest looks like in your region and in the specific imagery. And when then you apply the trained model to another image, what happens is that you see the results as a layer that highlights on the detected areas. So you can see the amount of probably deforestation that you will have in that area. And you can also see then the results, aggregated analytics, and filter by confidence if needed. The same can be done in another scenario, for example, in an urban scenario, where you have, let's say, or you would like to count, for example, the solar panels, so impact of the change, energy change inside your city. After training the model, it is applied across a larger area, and that turns manual mapping task into a repeatable AI-assisted process. Now, we move to the second example, it's the data storytelling that you see here. There is a no-code. It helps create interactive data stories, so Earth observation, climate, and statistical data becomes accessible, also to non-expert users. With their Copilot assistant, you start from natural language. In SKI, you can pick a suggested prompt, type, or use voice, and then you can visualize or edit the story. And it's operated by HaDEA space system. Now, you would have a video here, which is not here, but we will see later on. So, next one. So here you see their Copilot directly with the Ask AI interface. You can suggest prompt, type, or voice. And after you prompt, it starts preparing a sample story. No code, you don't have to do anything. Upon it is finished, you will have the visualization of the story, the output, and you can start editing the story to refine the message that you would like to send. So the goal is to make complex Earth observation climate information usable for non-expert. Next one, please. So, but we have seen now how easy storytelling can be today. Well, here we should be a video. So, yes. So now the next is simple. We want to move from the conversation when it becomes the interface. So first we connect. So the assistant is connected to data sources and tools. Second, we do and we ask. Instead of searching menus, just you type what you want to see. In this video, you see an example of the globe. You ask for layers like methane, ozone, dust, and the platform fetches them and renders them directly on the 3D view. But it goes beyond climate layers. You can ask other domains, like socioeconomics indicator across countries and years. Your system builds clear comparison, maps, and charts inside the conversation. And then you start analyzing it. You produce results you can use. And then you move to the next step. You insert. These outputs, charts, widget, maps, become a story element you can keep and reuse. You can even pull real-world satellite imagery using everyday language. Need to see the latest satellite scans of a specific region? You just ask. Want to see an actual image of Rome from last week? The system fetches exact Copernicus data and processes it right before your eyes. So one simple conversation to unlock very complex data. And this is the direction: connect, ask, analyze, and insert. So we will demonstrate the next step, which is the one that we just showed here on the video, into the next DestinE user exchange in Brussels in June. So I would, if I would be you, block the calendar, and we are looking forward to see you there. Next slide. But now we are at a turning point. We are moving from AI pilot services to decision workflows. And in that moment, trust becomes the bottleneck. So the question becomes, how do we move from raw Earth observation data to AI-based services that European citizens and public authorities can trust? For me, trust is not a slogan. Okay. First, traceability. We can explain what data and methods were used and why. Second, repeatable validation. Results can be checked, measured, and compared. And third, governance and compliance. So transparency and accountability are built in from the start. And this is why trustworthy AI is not a central topic in this workshop. It's now a central topic in this workshop. User needs and when and how AI is used in Copernicus data service is a key element. But trust must travel through the full AI stack, not only at the user interface, but from the data to the compute, to the models, to the validation, and finally to the services. Because if you want industrial AI services that are not only impressive, but also operational ready, we need to think in a complete stack. We need a coherent AI stack to build, deploy, and scale trusted services, and to bridge innovation to industrial operations using reusable, interoperable, and integrated assets. The AI stack has to be tailored for the domain, but still taking in advance all the synergies and opportunities that current AI European framework is offering, while being aligned to the European AI strategies and initiatives. Let me walk around the wheel of Earth observation. We start with a data and training data set. If that is not optimized and usable for AI, everything above becomes fragile. Ensuring alignment with the European data spaces together with EUMETSAT, introducing domain-specific aspects like spherical data in collaboration with our colleagues of ECMWF are all key elements. Then we need to compute and orchestration. Because Earth observation AI workloads, like many others we heard already before, are heavy, and they must run across different infrastructure, commercial and institutional, national and European HPC, AI factories, and projects like Simple and the Federation Platform are all elements empowering us. Then we have models and foundation models. This is where European innovation can create domain-specific models that really understand Earth observation and climate data. But models must be proven. So we need benchmarking, validation to measure performances, accuracy, and repeatability. Next is acceleration for developers and industry, model zoo and training pipelines, so companies and developers can reuse the building blocks instead of reinventing everything. Then we have embeddings and agents that help reduce complexity. Embeddings simplify downstream tasks, and agents can combine multiple steps in workflows. At the top, we reach AI system and services, what users actually consume. Now, two elements sit across the wall, across everything, governance and compliance. They must be built in from the start, not added at the end. And finally, it is not static. We must maintain and evolve the stack over time, data, models, pipelines, benchmarks, so the service stays stable and reliable. That is the idea of the ecosystem, something that is alive. So I will close with one question. Yes. So how do we translate AI-first building on European solutions into concrete actions that empower EU industry to deliver trusted Earth observation AI operational services? I will be very honest, I don't have a magic answer to this question, and probably no one here has. But what we need is a dynamic collaboration among all European stakeholders. Industry, institution, science, policy, user, the so-called co-design. And we must measure impact, learn first, and adjust courses as industrial scale trusted services. Let's keep working together. And I think that this workshop is a very good example, and focus on actions that are effective and implementable, because it is a marathon, it is not a sprint, from Earth observation to Earth conversation. Thank you.
Thank you very much. Luca, as before, I can take maybe one question from the floor or online. Is there anything online? Yes, please.
The question, oh, it works. The question is about the large language model that you're using for this application.
Yes, so for DEA, for example, we are using Llama at this moment. And we are looking forward more and more also to implement and use, let's say, European-based large LLMs, let's say. It's, let's say, our key towards Europe first, yes.
Okay, thank you very much. Another round of applause to Luca Girardo from European Space Agency.
Thank you.
And then we move to the next presentation. It's about the AI revolution in oceanography. It will be Quentin Godel, who's working in Mercator Ocean International. Please, the floor is yours.
Can I have the beep?
The clicker, yes, yeah, it should work now.
Okay, thanks. Thank you for the invitation. So I'm Quentin Godel. I'm working at Mercator and I'm representing my whole team. Okay. So I will focus on machine learning for ocean forecasting. Just waiting for the presentation. Yeah, so at first, let's just have a So the forecasting problem, what it is. So in that challenge, what you do is, well, we try to, from one state of the ocean to predict the next step of the ocean across several variables. So we are talking about the temperatures, the salinities, the currents, but also other variables related to the biogeochemicals of the ocean. So the chlorophylls, the ice as well. And we can predict from 1 day to 10 days to seasonal, but today I'm going to focus on 10-day forecasts. And I'm trying to remember my slide. So basically, with physical system, well, you heard it before, so I won't let it go into much detail. So it's better because we better understand it from a scientific point of view. But they are quite costly in computation. And they are not really, let's say, in the ocean, where you have not a lot of observation, it's not really easy to encompass, to correct the model with this observation. When you have a lot of observation, it's more easier. For us, it's quite difficult. But what the machine learning promise is that with with observation, I'm sorry, I don't.
We can wait for a moment. Yes, just wait. I think they're trying to put it on. Yes. I propose that we break for 5 minutes while they put on the new slides. So let's break for 5 minutes and then we'll start again with the presentation.
Okay.
Thank you.
Thanks.
So we are ready to start again. I give again the floor to Quentin Godel. Sorry again for the logistic issue, but I hope that now it will work. Please.
Okay. Okay, so I won't go too much into that. So equation resolving system against machine learning system. You heard about it, the advantage and the pros and the cons, basically. But one other thing is when we are talking about the ocean, we are talking about forecasting the whole depth of the ocean, not only the surface. And the difference with the atmosphere is first that the water is denser than the air. So there are many phenomena that occurs at really, really tiny scales. There are larger phenomena, and there are phenomena that actually occurred on various scales, from tiny scales to have impact on larger scales directly. Another thing is the land is something, the bathymetry of the ocean, the bottom of the ocean is something that it's quite difficult to deal with, and especially with most of the machine learning architectures that we know today. And finally, well, we are talking about machine learning, we are talking about processing a lot of data, but we don't have much observation data on the ocean. We have a lot of observation for the surface, but for the depth, it's really another deal. So we need to find a new way of evaluating the machine learning systems so that we make sure that they respect the physics of the oceans. So this is why, actually, the machine learning came to the ocean domain later than in the atmosphere. And we were there at the very beginning with other researchers. So I will talk briefly about GLONET and HaDEA. GLONET is the model that we developed at Mercator. So, well, I guess you know that in a neural network there are several layers, and our models, well, he had a layer about capturing the temporal propriety of the system. Then we have another layer that is based on Fourier operators that captures the small scales and the large scale phenomena of the ocean. And then we have an autoencoder that is actually capturing the multi-scale thing through the multi-scale phenomena through a light and space. So I won't go into much detail on that, but I will do a demonstration tomorrow if you want to check that. Okay, so our model, GLONET, is forecasting the temperatures, the current, the salinity, and the sea surface height for 10 days. It has been trained on Copernicus mine data, so the GLORIS 12 dataset, and it had been taken like 1 month over GPUs that are available, that were made available from the ECMWF data centers. And for 10 days inference, it takes, well, in good condition, it takes 3 seconds in a good GPUs. But if you have like a smaller GPUs, it takes 30 seconds, and even on your laptop, it takes 7 minutes. And in comparison, such forecast takes 10 hours on HPCs for the physical models. So there is a huge gain there. And finally, if you want to reuse it for the whole year, let's say for reanalysis and so on, it will take only 3 minutes to produce. Something that is interesting is that it has been trained on a really, let's say, a 12 degree resolution models, but the output grid is 1/4 resolution. So the grid itself has less resolution, but it has been trained on a high resolution model. So if you interpolate in a naive way from 1/4 degree to 1/12 degree, you get something that are really similar, and that's why we call that it has an effective resolution of 12 degrees. And once again, I will demonstrate it tomorrow if you want. So I'll talk about GLONET. There is another model which is called HaDEA. It has been compared in the literature with GLO12, which is one of the main model in operation, forecasting system in operation as part of Copernicus Marine. And we needed then, when publishing GLONET, to compare to CHIHE and GLO12. And let's say the common way to do that is by comparing your model with reference model, let's say the physical model, or comparing to observation. And I will demonstrate that no, in our case, it's a bit different. We need a smarter way to do that. So here, so bunch of graphs, but trust me, there is not big difference, big deal between systems, okay? Either sometimes there is one model that is slightly better for the current of the surface, for example. Another time it's for the temperatures, the deep temperatures. But there are not like huge difference between models if you compare to reference models or to observations. But when you look at the data, here on the right you have the ground truth, so the glorious 12 a glorious 12 snapshot. So yeah, it's kind of continuous. I mean, if you know the ocean, you know it fits well. On the top left, you have the GLONET system, our system, and it's quite similar. But if you look at the bottom left, you have the CHIHE model. Here, if you look at it, you have matrix-like artifacts there. So that means it means nothing for an oceanographer, okay? So to capture these errors there, we define new metrics based on detecting the geostrophic currents, so large-scale current of the system that are not directly visible in the forecasted variables, and also the mixed layer depth computation. And when we compare the scores for that, well, there you have a major deal. GLONET respects the physics and not CHIHE. So GLONET, in a nutshell, it has been trained during 2024. In the late 2024, it has been put in pre-operation on the EDITO platform, which is the digital twin of the backbone for the digital twin of the oceans, the European one. It produces daily forecasts. You can access them, you can download them, you can browse them in the MyOcean viewer. And since a few weeks now, you can run them on demand on EDITO on your space there. And going back to the timeline, well, the whole weather community were gathered around a benchmark which is called WeatherBench. They are new initiative now, as our colleague from ECMWF mentioned just before. But we decided to do another benchmark to gather the whole ocean community there. So it's Ocean Bench. It's available right now. You can, if you have a system, a forecasting system, you can just go to Ocean Bench, the website, follow the instruction, and you can benchmark your system against other models that arrived and against metrics that matter to make sure that your ocean respects the physics. So we included all the metrics that I mentioned before, but even more. It's an open and collaborative project. There are many people already that contacted us to be part of that, and it will evolve over time. Okay, and a few words about other works and future works that we have. So I mentioned only the physics of 10-day forecast of the physics of the ocean, but we are looking at the biogeochemistry, the ice. And the more it became complicated, the more we have to be smart about how to use the GPUs. So actually, we are not talking about big data, we are talking about heavy data. Every snapshot of the ocean, every state is a heavy piece of data. And if we want to make like a relevant training, we have to, well, to think about it and to adapt. And it's actually lead us to really the heart of the machine learning science. So it's really interesting. And of course, we are looking at climate forecasts, seasonal forecasts as well, and better way to assimilate the data that we have, and other tools so that we can produce high resolution forecasts, either in days to hours, and also in terms of spatial resolution. And thank you.
Thank you. Thank you very much. So there is time for one question, either from the floor here or online. No, I have a question myself. So do you actually cooperate with other international entities that are dealing with marine activities in this artificial intelligence comparison and work, or you're working just on your own in that respect?
No, actually, we visit the people from the CHIHE, the other model I talked about, we visit them. So yeah, we work with them basically, and the other models, it's the same. There are other models also in Germany that we are working with. And for the ocean bench from the Earth, I mean, if you look at the papers that we published, like it's a melting pot of plenty of institutes.
Thank you very much. Again, another round of applause. Thank you for that. And now we move to the last part of this session. I will call on the stage Isabelle Benezet from France and Andrea Taramelli from Italy. I know them quite well, as they are participating a lot in our committees in Copernicus, but at the same time they participate in Destination Earth Copernicus committees. So please take a seat, so it will be more interactive now. And the reason for this session is that we like to have a little bit the national perspective about what we have heard, but also what has been the evolution, what are the plans in the years to come. So I will have a couple of questions to both of them, but if you have more, you can also introduce them online. But the first question I would like to give first to Isabelle and then to Andrea is, can you give some examples on how artificial intelligence or machine learning revolution has developed in France, in your case, in the area of Earth observation? Isabelle, please.
Thank you, Mauro. Yes, we in 2018 we developed a strategy for AI in France to secure the national research ecosystem, and in the second phase was launched in 2022 to spread AI throughout the economy. So training and research, support for state-of-art offerings, bringing AI supply and demand closer together was the lever we used to achieve this goal. And of course, the field of Earth observation was very important, interesting for us to explore, because it's a major, it's at the center of major scientific challenges such as climate change and water resource management. And we federate the community around a structured ecosystem, central around national research organizations, environmental data infrastructures, high-performance computing capabilities, and a federated national organization connected to European programs, and such as Copernicus, DestinE, and EOSC. So, coming to artificial intelligence, we put in place a priority research program and equipment for artificial intelligence. And in this framework, France invested 560 million over the last 2 years to develop this research program, and also AI clusters and computing storage and facilities, as also Earth observation data infrastructure like Data Terra and Geode, and we invest a lot of on this infrastructure. So it's a very important investment for France, and I can give you an example. It's about the forest. We develop a priority research program and equipment dedicated to forests, but we have also developed some this kind of program for water management. And thanks to the data coming from Copernicus and specifically Sentinel-2 data, but also LIDAR data and in-situ data we have on the field. We now are able to run a machine learning model, and the result was we detect water stress of the forest at an early stage. We also identify pest attacks before they become visible to the human eye, and estimate biomass and carbon stocks with increasing accuracy. And finally, simulate the adaptation of tree species to future climate scenario. And what is important, in this case, it's that we have observation, and now on fields that are not easily to modelize, we have prediction, and these predictions are very helpful for decision making. So this is the example I chose to develop.
Thank you very much, Isabelle. And now the same question to you, Andrea. What's happening in Italy? What are some examples?
So, Mauro, thanks for the invitation. I start from what we have done starting from 2018 and 2020, where we built, before the COVID comes, the National Space Economy Plan. Within the National Space Economy Plan, there was a fully dedicated part on the Earth observation. But it was, the approach was really user-driven. So we identified the 8 services, and within this master plan, there was all the different thematic area, including the AI development. So when the COVID arrived, and Italy, you all know that we got the next generation EU, it was quite a big investment. We had a plan of something around 4.5 billion euro on the Earth observation. So it's almost, let's say, known the EURIDE investment that is only, sorry for the only, it's 1.3 billion. All the other investment were sort of around like 500 million on the AI development, on the building the HPC infrastructure that is not only based in Bologna, but is distributed now in Naples, and we are structuring also in Rome. Because we have built the fact that if we were going to increase not only the Earth observation from satellite, but also the in-situ network that is around another billion for the in-situ network, we need to develop also in the services, also the AI development and so on. Another investment, and then I will go to some example, practical example. Another investment was also, build up a new generation. So we were building what we have called the National PhD program, focused 2 of them on AI, because we had to cover the development of young generation on that, and other 2 master PhD program on Earth observation and space science. So these 4.5 billion were covering what are the thematic area, not only building the, let's say, use cases, because what we were trying to give with the master plan is not just go on the use cases. I'm always underlying in the discussion we have, not only in Copernicus, but also in Destination Earth, that is not operational. So it's the Euro HPC is not giving to national civil protection or European civil protection an infrastructure that is really operational, as Copernicus is. So what we have done with the plan is how we can build a line. So the 4.5 billion were, for the services. So the driver were the user requirement and the services, and then the upstream part, but also the development of new AI technique. Because what we have in mind, and in the precursor stage, there was not infrastructure and AI based in Italy that were able to process and to make them operational for the operational national civil protection services and so on. So 2 examples that we are delivering, and this was done also in discussion with ECMWF as and so on, was like, that we had delivered an official primary law in 2018 to build up the Met Office in Italy. We didn't have before. There was, only the Air Force Met Office. So in this roadmap, we were trying to to make a new civilian Met Office, and how we can use also, in the discussion we had a lot with the ECMWF, was how can we build not a Meteo France, because we were too late for building up a Meteo France. We are too small and too late. So how we can cover the gap. And the discussion was we can cover the gap with the AI and with the new system that we were building up. This is one of the real example that where we are using this, and I'm taking from Carlo Bontempo the leapfrog example, how you can build a Met Office when you don't have one, using the AI investment. And the other one is considering the Raw Material Act. We are building up an infrastructure using AI to, to map and to, let's say, oil and gas exploration and mineral exploration, fully based on, hybrid and AI model, based also on this new development, that in the Area constellation there will be 5 hyperspectral, then how we will use CHIME and so on, how we can build this new investment for the implementation of the Raw Material Act.
Thank you very much. So we heard this morning how artificial intelligence is getting more and more in everyday's life with the presentation from CONNECT, but also how it's very linked to Earth observation activities through the presentation of the ESA, ECMWF, Mercator in different areas. So you have shown some examples, but I think indeed we have to look into the future. Where do you see opportunities for evolution, but also showstoppers into that? You already mentioned, for example, the lack of operational HPC, and eventually how Europe can help into that. Isabel.
Thank you, Mauro. Yes, first, maybe we heard a lot this morning, so it will be quick. I think we can use artificial intelligence for fusion of data coming from the Earth system, and I think we can really benefit of that. Maybe Earth modeling, because we have, and we see this morning, each part of the Earth system, atmosphere, marine, but what about the overall? What about all the world, the Earth modeling, because of the AI, it's maybe a dream, but maybe it could be, it could happen. Why not? And the development of specialized European Foundation models for Earth observation, capable of being adapted to a variety of sectorial uses, from agriculture to civil security. I think it would be great to have this kind of tools available and capable of adaptation. And the growing integration between high-performance computing embedded in satellites, and embedded AI also, and apply this strategy to all sectors we are involved in, and we need to have solution in like water management or maybe modelization, the biodiversity, that is complicated. On the obstacle, of course, the first one is fragmentation, because we are Europe. We have national priorities, we have a fragmentation of funding and infrastructure also. Access to large scale of computing capabilities, like said Andrea, it's complicated. Training advanced model requires HPC and cloud resources that are competitive with the world's major power. So we have to be sure to have this. We have also an issue that was said this morning of technical sovereignty. And for now, we have dependence on critical components, non-European crowd infrastructure, non-European models, and we have to solve this. It will maybe take times, but I think it's a challenge we have to solve. And skill remains central also, of course, and not only digital skill. We need skilled engineer who understand Earth modeling physics, remote physics of remote sensing, and deep learning architecture, of course. So, do you want me to go on European?
Yes, yes, please.
Yes.
Yes.
So what we think between the complementarity between what we did at European level and in national level, we think that at national level we have to work on agile and quick things to do, like startup funding, fast experimentation and POC, partnership between space agencies, universities and industry, and training in university and digital engineering schools. At European level, we have to develop infrastructure and measure structural programs, and to share data platform, interoperable sovereign clouds, and shared Earth observation, like we did with Copernicus. I think it's very important. Open source European AI model dedicated to Earth observation. Also maybe joint training and talent mobility programs. It's the twinning between the national and European level must function at a virtuous circle. Innovation emerges locally or consolidated at national level and then becomes industrialized and at the European level using European infrastructure.
Thank you, Isabelle. Andrea, the same question to you. How do you think the possible evolution and showstoppers, and what could be a synergy with Europe and where Europe can help?
I start from the last part of Isabelle, and also one of the first point. One of the main problem of Europe and from the member state, because Europe is member state, is the fragmentation. So already this meeting shows that the fragmentation also between the European Commission is not coming to an end, but at least to a discussion that is already something that is really appreciated in that sense. As again, Isabelle was saying, when we have an Earth system, it's not separated by thematic area and so on. It's an Earth system, so you put in the same line climate, ocean, and so on. So we have to figure it out. And again, what is well developing under Destination Earth is an improvement on what Copernicus is already doing. So we see the improvement, but then we have to go on that line. So what member states are asking to European Commission is going to that line. So making clear who is developing the HPC, the infrastructure and so on, and what is building on the top of an operational system, not the vice versa. What we are always saying in all the different committee and expert group is the fact that the end users is becoming confused about where I'm going. DestinE, Destination Earth, Copernicus, the users, it's the same. So he's always asking, so are they closing Copernicus and I'm going to Destination Earth, or I'm going to use Destination Earth? So it's very confused by the fragmentation offer. So this is something that we ask as a member state. Vice versa, member state has to contribute to not a fragmented type of approach where member state comes to oversell what they are doing, but how we can build in the domain on what is under development with AI and so on, or also in the evolution of Copernicus, what can be a contribution in terms of like a program that is not overlapping. Again, the example of IRIDE, we are developing, and some of the satellites are already launched, a system that is not overlapping what Copernicus is offering, but is a sort of like an integration that can be optimized on Italy, but that can be used by other member states and European Union itself. And it's based not only on user requirement, but also on the, as again Isabelle was showing, on the fact that how we can use artificial intelligence processing on board to have low latency and some other information that right now Copernicus cannot deliver in that sense. So how much the artificial intelligence on board and also on the ground system can really improve the latency, that is one of the key issues for the not only the Met Office, but for the National Civil Protection. That was something that it was always underlined that Copernicus and also DestinE cannot cover. So how much this in the onboard processing domain can really improve the offer that the European Commission and the member state can twin. I can make another example because even if it's not under discussion today because we are talking about DestinE Earth and Copernicus, also the new development, it could be Earth observation, governmental services and so on. How can this new development at European level can integrate, not overlap or just be a shortcoming for Copernicus and so on? So in this sense, again, how much the artificial intelligence can cover some new development that we are discussing as a member state with the European Commission in that sense.
Thank you very much to both. Are there any questions from the floor, or even, some comments that you would like to raise? We have here two representatives from two member states. But again, if someone would like to have a comment or a question, or online, I don't know. There is one online. Yes, please. Yes. In the audience, is there any request for a question? I made my questions already, so this is your time if you need. Let's take the. Sorry. Are there questions already on Slido where?
There is one question for Isabel.
Yes.
Regarding the AI for biomass estimation, which input data was it based on? Where could further information be found? There were some typos in the question, but
sorry, I don't.
So they want to know on what information the biomass estimation was based on. So what was the input data that was fed into the AI model to derive biomass estimation?
About for forest?
Yeah, in your forest example.
It's Sentinel-2 data first. We have a campaign of measurement with LIDAR that I mentioned, and also in situ data that was also it was a special dedicated campaign of measurement for this.
Thank you. On Slido? Okay, only this one. Okay. Yes, please. Can you introduce yourself and then and then ask?
Yes, of course.
Thank you.
Jorge Gomes. I'm from the Virtual Operations Support Teams in Europe and Portugal. And my question is for the both of you, actually, because how can we replicate this in countries that are more data poor? Because we have this divide of data-rich countries in the European Union and data-poor countries in the European Union. And for instance, in Portugal, we have lots of data about forest fires, but we don't have enough data about forestry, for instance. So how do you see that we can actually, with AI, use these models to replicate these solutions that you are applying in your countries to other countries in the European Union? Thank you.
I have another part of my presentation. I shortened it, explaining how we use it also for in the framework of an international program called One Forest Vision that is made with artificial intelligence. We map the forest specifically in Africa and in the Amazon, because the objective was for climate change. And in this framework, we produce tools for partner countries for allow them to track deforestation and illegal deforestation, and also we provide indicators that allow to it was trustful indicator we are used for the climate change commitments and by the country concerned. So I think it's quite possible to share and to open up the circle, and maybe you have to take some contacts with the teams in charge of this. I will take you my card, and we will, if you are interested in.
As I was telling at the beginning, when we built the plan, we were thinking, I make the example both to, let's say, raw material and also agriculture. So we are setting up the innovation also using artificial intelligence, using what are the available data right now as a precursor. So we have, let's say, both Prisma and Nmap at European level. But the idea was to build up the system with these two precursors, but already looking to what CHIME is going to deliver. So in that sense, what we are implementing right now can be implemented also in other member states, because Prisma and Nmap are available, with the same more or less kind of availability. In that sense, when we design the IRIDE constellation, we were thinking to then share at least the 50% of the spare availability of IRIDE. Of course, it will have a cost, but it's not going to be. But it is really designed how it can be complementary to the CHIME operational Copernicus mission. So the idea is to develop something that then other member states will be, impossibility of taking in charge, because it will be based both from CHIME as a Copernicus evolution, and then integration of the 5 satellites that are going to be launched next year by IRIDE. So, and this is going to be applied to the raw material and to the agricultural sector. Actually, we were, starting from what are the HP high priority candidate products that we have, defined with the mission advisory group with ESA. So we were not reinventing the wheel, but really looking on what ESA and the Commission were developing on CHIME, and then how we can integrate using also machine learning, so a hybrid model or full machine learning. And we have both publication and also, official reports that can be shared absolutely. So do consider that is based on the development that we will have both in Copernicus and, in the sort of like contributing mission that will be available within IRIDE.
Thank you very much. I think with this we round of applause to our guests here. With this, I propose that we conclude the session that we had, session 2 that we had this morning, and Mitch can drive us through the next. So if not, I can say so lunch is outside here or on the top of the stairs, just outside here. There is the room for demonstration that is available. As said in the beginning, please, we have been really asked not to bring food into the demonstration room, and also in this one. And then you are welcome back at 2 for session number 3 that will be about big data and high performance computing. Mitch?
Thank you, Mauro. You said it all, almost, but you forgot about the chocolate. We are late, but we take the blame this time because there was a small technical glitch. Another small remark on the slide. Of course, there were many questions online. We just picked a few of them, but we will run the questions to the concerned people and answer to them offline, and we'll publish also the answers on the meeting website. Thank you. And so let's reconvene at 2 p.m. sharp, please. Thank you.
Okay, good afternoon. I think we can start, well, or give it a couple of minutes because participants are still arriving. Hope that you had a good lunch. You came back re-energized. And I have to say that I'm always wondering which is harder, to run a panel just before a lunch break or just after a lunch break. So we see. We promise you a lively discussion at least. I think we can now start. And again, good afternoon also to the participants online. It has been a very interesting morning. So allow me to introduce myself. I'm Babis Tsitlakidis, and I'm the head of the Destination Earth sector in DG CNECT. And as you have seen already from the agenda, this is a panel and a session on big data and high-performance computing, which is about really how these building blocks, or foundations, if you like, so supercomputing power, a lot of data, our workflows can really help us to progress, go beyond what we know already in terms of AI modeling. And this will be the discussion today, and I think it's quite an interesting topic. I still remember 30 years ago when I first encountered AI, it was everything about algorithms. We used to work with programming languages like Lisp or Prolog. This is not the case anymore. AI is a lot about algorithms, but it's also a lot about what we now see as a revolution in this domain. And this is the power that high-performance computing and a lot of data that we have now, exabytes of data in our disposal to train our models. So it's quite interesting to see how we can really use them so that we can scale, as I said, and we can make progress from where we stand today. And for that, we will have also the help of a lineup of very distinguished speakers. The session will start with 3 presentations, and then we will have an open discussion with 5 speakers, so 3 + 2 that will join the panel. And then our speakers will share their current experiences, but also their perspectives on how we can really accelerate innovation and impact in the area of Earth observation and Earth system modeling. So I'm really sure that this session will spark this discussion, and you will have, of course, the opportunity both here and online to ask questions via Slido, or you can raise your hand and we will give you the floor. Hopefully we will manage also to get some chocolates, Mitchell, no? So let's see. I will be firm with the speakers. So without further ado, allow me to ask the first speaker to join. The first speaker is Tiago Quintino, who is the head of software development section in ECMWF. And Tiago, you will speak about an end-to-end AI stack for weather and climate, from big data to product delivery, which sounds very promising. So from data to delivery. The floor is yours.
Hello, good afternoon. Thank you for inviting us here and welcoming us so well. I guess I have the task of keeping you awake after this nice lunch. Hopefully with the power of the clicker, I'll be able to move my slides forward. Can I see my slides, please?
They are coming.
Should have brought some juggling balls that could keep you entertained. Maybe someone took a longer lunch break?
Yeah, it looks like. Someone to check where. Well, at least you are used to it from the morning, so you know how it goes.
It's possible that it's my presentation because it's big data, so
yeah.
It's only 120 megabytes.
That's why we need fast networks.
I was thinking, should I include the movie from DestinE or not?
Well,
it would be cheaper, it would be simpler without the movie from DestinE. It's what you get when you do these high-resolution movies, you know.
Yeah. Hopefully it will come, but...
There you are. Very good. It's coming. Something is coming.
I'm still thinking about the chocolate, so you will give us at least 5 minutes more.
Do they come with the coffee? Oh, wait. Yes. Almost there. Full screen, please. Is that... Oh, it's like a web page. Okay. I cannot click.
Apologies for this delay. Hopefully we will start very soon.
So we can't talk from the back. It's only possible like this. The other one, the full screen is not working.
Full screen is not working?
So we have to go like this.
But I cannot turn, I cannot...
No, because now we have to switch the computer.
Aha.
So
I also don't have slides turning.
you will need to...
I guess they will change slides.
Yes, I think you say next.
Say next.
Okay, there are lots of animations. Okay, I will beat for sure Matt's record this morning saying next slide. Absolutely, for sure. Okay, next slide, please. Okay, so very quickly, I'm Tiago Quintino from ECMWF. Matt already presented what ECMWF does. I just want to highlight to you that aside from, of course, our participation in 2 of the Copernicus services and our participation in DestinE, we also have another also quite important job, which is to run 24/7 operations, and that is 4 forecasts a day. And that number will be important later on. My presentation has lots of numbers. Sorry for that. No equations, though. Next slide, please. Okay, and please click through many times, at least 4 or 5 times, so that we don't... okay, once, twice more. Thank you. Okay, so let's talk a little bit about big data. And to understand big data, I'm going to use the ECMWF pipeline as an example. Because if there is something that machine learning is changing, is this definitely changing the way we do our mission for 50 years in serving weather forecast data to our member states and clients. And this is the current pipeline, production pipeline of ECMWF. We take observations from around the world, about 6 terabytes per day. We ingest that observations and we create the initial conditions of the atmosphere and the Earth system. We run a model that produces per day 400 terabytes of data. This number is correct, 400 terabytes. 4 times a day, 100 terabytes, okay? That's the forecast. And from that forecast, within minutes, we are reading nearly all of this data, okay? And we are producing from there to 92 terabytes of products that are disseminated around in Europe and around the world immediately. So we are talking within 1 hour from start to end, okay? And aside from that, every day, especially with now open data, is very popular. People also pull from us around 46 terabytes of data just from our forecast. Nothing of Copernicus of DestinE is including these numbers. These are just our core mission of numerical weather prediction. And this goes to 1,100 dissemination destinations around the world. And every day, about 640 terabytes are added to our archive. That's close to a petabyte per day. And of course, is more than the other data because there is also research data in the mix. And that number actually includes also Copernicus and DestinE and so on. So, the next slide, please. And next slide, and next slide, and next slide. 3 clicks, please. So let's talk a little bit about big data. Big data was a buzzword about 15 years ago, and it came with these famous 3 V's of big data: velocity, volume, and variety. And then later on, someone added veracity, and then became the 4 V's. But the important thing to understand in this world of AI is that data is the new oil, okay? You wouldn't have LLMs if there was not the data availability in the internet to train them. And in our world, and one slide, please. And in our world, the data we have to feed our LLMs for the Earth system model is crucial to make them accurate. And this quote here from Andrew Enge from at the time he was in Google, if AI is the rocket ship, data is the fuel. And it didn't mean in the sense of the essence of why we need data, but he was trying to say the fuel needs to be of good quality. Okay, so the quality of the data is very important. Okay, so next slide, please. In that sense, I'm going to talk about 2 more clicks, please, and I'll go to about three challenges we are facing. Oh, back, thank you. 3 challenges we are facing. We'll talk about how to prepare and feed data to AI training, how to adapt to data production, the data production pipeline, so that's the inference part, and I'll touch very briefly how to handle AI data heterogeneity, because that's a big topic and needed a whole different talk. So let's get started. Next slide, please. How do we train, how do you prepare and feed Earth system data for AI training? It's important to understand this because it is an issue of data quality as much as it is an issue of volume. Next slide, please. ECMWF's archive has been growing since we were founded 50 years ago. This slide goes back to 1978. And you see here the growth of our HPC next to the growth of our archive. This is a logarithm scale. And the 2 lines are strictly parallel, okay? This means that ECMWF is a data producer whose main producing engine is the HPC. And we archive what we produce. And therefore, these 2 lines are nearly parallel. Okay? Next slide, please. Let's change scale. Just to say, this is equal to, back. This is equal to 40% annual compound rate. I know every one of you would love to have that on your bank account. Imagine 40% every year from the bank, right? This is what we need to deal with. So next slide, please. We change scale. And now we go to the real scale. This is you see the exponent of the growth. 1 more click. And the top sits at 1.46 exabytes of data. Now, that's impressive because it's a big number. It's so big you really cannot think about it. Like, it's like millions of gigabytes, right? And billions of gigabytes. And it's very quick to say exabyte, but it's as quick as saying terabyte. But there are many zeros in difference of scale. 1 more click. What's really, really impressive is that we not only have the largest meteorological archive in the world, all the data is indexed and all the data is accessible and it's very much active. We read from our archive 510 terabytes per day. So we write 640 and we read 510. Very few other places in the world have an archive this active. We have an archive that is so active that we have to change tapes quite often because they were down due to mechanical failure. So we read way too much from the tapes. We use tape systems like you use your hard drive in your computer, okay? So why is this important? Please, next slide. Is because this is intimately linked with how we access data and how we make sure that all the data that we produce is still addressable and accessible, and also relates to the fact that high quality data is very much sought after. So ERA 6, through the Copernicus, ERA 5, sorry, through the Copernicus service, was this massively influencing data set for the Earth system modeling, has become the foundation, basically, of the AI revolution in our community. It is used by nearly every model that you see out there, and ERA5 is 11 petabytes today, and still growing because obviously we keep adding to it. But ERA6, just the start, just the historical part of ERA6 is going to be 30 petabytes. So we are going to increase the resolution, and that is not multiplying by even more because we are adding some new compression mechanisms, etc., to keep the cost down. But what's important is the quality is there. Our scientists in our community has worked enormously to make this high quality, and we now need, the technologies like me have to bring it now into the use. And how do we bring this to train? Next slide, please. We have a pipeline of data to users. This is what you are seeing today. We have our archive, we produce the data, we put it in our storage system, we feed it to the user. We have these things called the data stores, which in DestinE we call it data bridge, but it's more or less the same thing. It is a system delivering data to the users close to where the HPC is, where the data is produced. And next slide, please. These data stores are very popular. In the case, for example, of the data stores we run at ECMWF, we have 250,000 users registered, 6,500 daily active users, pulling out about 500,000 requests per day. 500,000 requests per day. And we serve steadily 115 terabytes a day. This is 115 terabytes a day is Copernicus only data, right? Just Copernicus, 115 terabytes a day getting out of our data center. And a lot of it asks for post-processing. A lot of it is a 24/7 service. So a lot of engineering and technology has gone to make this scalable in order to reach the users. But that was before the AI revolution was there. So what can we do, or what have we done to make this even more accessible? Next slide, please. So Matt this morning touched base on this. We have built Anemoy, this framework to help train models. So it's the framework because you can make your own model. It's open source. You bring your ideas in, and you use this framework, these tools that are there to make your model. Matt was way too modest this morning to point out that received a Best Technology Award last year. And it's a fantastic technology with a lot of European partners coming in and contributing. And I would really say it's a fantastic example of what Europe can do at its best, right? Next slide, please. So Anemoy is this framework where you have a defined way of building data sets. So it has all the tooling there to help you build your training data set. It has the Anemoy core, which has the components for the model itself, so the training, visualization, model, networks, all the machinery you need for an AI model. And then at the end has a mode where you run in inference, right? You take the model, the weights of the model, and you deploy them in range. And you can see there the amount of the very diverse amount of research institutions contributing and Met services contributing to this. Next slide, please. But the challenge really, really is how to get the data to training, okay? And please bear, if there is one slide I would like you to take from this talk is this one. AI training is an HPC job. I know we talk a lot about AI factories, but where is the commission putting the AI factories? Where the HPC centers are. Because it's smart. These are the people who know how to run the fastest machines in the world. And the fastest machines in the world, guess what? Is the GPUs. So an AI training is the HPC job. You need to put the data next to the HPC. GPUs are very, very hungry beasts. They need to be fed data constantly. And there are a few numbers here in this slide that I want you to pay attention to. The data set that we go and pull from the data stores, from the climate data store, atmospheric data store, our own archive, is about 10 terabytes. Peanuts compared with all the big all the big archive we have, okay? But you need to put it close to the GPUs because in a single training of a model, you are going to read it 100 times or more.
okay? And you need to feed those GPUs constantly. So you need to put this data as close as possible to the GPUs. If someone tells you an AI-ready data set is going to be sitting far away, it's not ready, okay? It is ready when it's sitting next to the GPU. That's when it's AI-ready, okay? Because that GPU is going to be so hungry. It cannot wait, and they are so expensive, we cannot afford them to wait, okay? Then for doing that, what did we use? We use anemoi, that's the symbol there, to frame the data in the best way possible, the way that the model needs. But to do transfer, to do conversions, etc., we use something else called EarthKit. Next slide, please. EarthKit is an environment, bit squished. It's an ecosystem with, oddly one of them survived, with many different components. And these components, they are things that do data transformation, meteorological computations, does interpolation between grids, shuffles data around, converts data, and runs workflows. Okay, so all these components are the things that are around, a bit squished there. Next slide, please. So that's how we are building the pipeline. That's how we are preparing the data. I'm coming back to this EarthKit a bit later, but can we go? We are now going to talk about how do we prepare the production pipeline, because production is a time-critical issue. Okay, can we go next slide, please? So we can zoom in a little bit to this production of ECMWF. 3 clicks more, or 4. Thank you there. And one more. Thank you. So if you look into ECMWF, what we are doing now, we are running 2 models, one physical, one AI model. And Matt touched on this. The physical model takes 2,500 nodes of a supercomputer, 1 hour and 20 minutes to run, and the same forecast runs on 51 GPUs in 1 minute 40. So this is the difference we are talking about. Matt talked about in energy 10 times more, but think about in time, think about in so many other criteria. It's a game changer, right? This is a jump we are going to see once in our lifetime, and it's equivalent from going from manual calculators to computers, right? Going from computers to GPUs is the same again, right? The jump is so big. Next slide, please. So, 1, 2, 3, 4 clicks more, please. One more, yeah, hold there. One back, please. And in order to handle this sheer amount of data, remember for the 100 terabytes every time we run a forecast? Now imagine those, instead of 1 hour, they take just minutes to arrive. The GPUs, they are hungry beasts in training. Guess what? They are also hungry beasts in giving you the data back. When they run in inference, they spit out lots of data, very, very quick. And we have then to absorb all this data. And we had a preview of this in DestinE. When we ramped up in DestinE the resolution of the model so much to 9 kilometers, 2 kilometers, we needed to rewrite how we did the pipeline. And that's what we did with this multi-O development, which is in-memory, asynchronous receiver of all this data and then processing of the data. In DestinE, we were putting it to disk because that's what was available. But 1 click forward, please. For AI, what we do is it will be anemoi, inference, providing all this data. And on the other side, instead of putting things to disk, we are going to feed it to a post-processing framework that runs completely in memory. Next slide, please. That's called EarthKit Workflows. And this technology was what was possible to see here, which is a bit jerky, but in this movie that you're seeing from DestinE, you see clouds like if you would be from a satellite, but this is a simulation. So this is hyper-realistic simulation of a climate scenario, okay? And with the accuracy is just mind-boggling. Next slide, please. But the data that comes with it is also mind-boggling. So in order to provide that data to users, in DestinE, we developed some new technologies. 4 clicks forward, please. One of them was Polytope, that allows you to go and pinpoint the data that you need
only the data that you need from the data sets of DestinE. And you just express, oh, I just want a country, or I just want, for example, next slide, please. I want a time series of the country. See? Yeah, I need to go. Yeah, we're near there. And then you can do a flight path, for example. Next slide, please. So when we pack all these technologies, 2 more clicks forward, 3, we get what we have building and you have outside on a demo, which is the forecast in a box. If you take Anemoy and you take EarthKit, those are the 2 engines that are inside of that forecast in a box. Outside is a hardware, but truly, the forecast in a box is not hardware. It is a software that anyone in Europe will be able to download, companies in Europe will be able to use for their own purposes, to run their own forecasts, right? So the idea is, instead of sending this a large amount of data to users, why don't we send the model? Give them the model so that they run it themselves. Okay, next slide, please. And we built these technology of building these pipelines to produce the products, the same products that we use in the same pipelines and workflows we use in our operations. We are packaging and putting them inside of the box. Next slide, please. And we are putting a nice GUI on top that people can click and choose their products. Next slide, please. And all that technology basically is 1, 2 more, please. 4, 3 clicks. Thank you. All that technology that is inside of the forecasting box is based on this creation of these graphs that describe all the work that needs to be done, minimizes the work that needs to be done just to provide the work of that the user needs, and generates these very complex graphs. That's actually a real one. And then you can execute that on an HPC, on a cloud service, on a user device. And that's what we have outside. Next slide, please. And we put it in a box. No, but this one, the really reason we have this outside is because it has a GPU inside. You only need a GPU. Next slide, please. I think just to say that we are also packaging with it our technology of graphical products, professional grade graphical products that the forecasters use in every country is going to be packaged together. The same thing we are using in Copernicus to provide professional grade graphics for Copernicus. Next slide. I'm going to skip this section here. 2 slides forward, please. We just to highlight that 3, 4 more clicks. Okay, just to say that all that we're building is following standards, is completely interoperable, works with ZAR, with X-Array, Pandas, Anemoy is one of them, with our own internal stack. The idea is that we are building something that is open for the community to work with, open for the community to contribute to, and just as with Anemoy, we're building a community around it. Next slide. We're going to skip over the next slides and go directly to key messages. 1, 2, 3, 4 clicks, please. So ECMWF has 50 years of experience handling massive data sets, and we are serving our users in a 24/7 operational resilience. We have brought that knowledge and packaged that knowledge into what Anemoy and EarthKit are today. With that, we are transforming Earth system data into big data sets that are already existing in our Aero HPC systems where we train our models. We are developing scalable training and inference AI stack that anyone can use. It's fully open, exists today. We have used it. We eat our own bread. We make it. When we use the things we use, we are putting outside. Nothing is hidden, no secrets. And all this is done in collaboration with member states, with the co-funding of the European Commission, and has led clearly to successful breakthroughs that show, 1 more click, that in my opinion, we can demonstrate clearly that Europe leads when it comes to Earth system modeling. Thank you very much. And
please take your seat. I hope you can hear me. No? Now? Now? Okay, now it works. Many thanks, Thiago. I don't know if we have questions in Slido, no? or in the audience? We have one, please.
Hello, yes. Thank you. My name is Matteo Battiuzzi. I'm working for the European Environment Agency in the Copernicus Land Monitoring Service. Very interesting presentation. You said, and maybe I missed that, but you said this model can be downloaded and can be used if you have a GPU.
Yeah.
There are many GPUs just because they are high-end and normal GPUs, sorry. And there is also a question, have you considered eventually to have this like an API service to access this model? Thank you.
Very good question. So when it comes to the GPUs, I would say the memory is more the concern rather than which GPU. Of course, there are some GPUs that are going to be run faster. The memory, you need to have enough memory to fit the AI model in. Yes, and moreover, because this is more than just the GPU running, the model, it is also the post-processing pipeline. You have to also have memory for the products, right? For the output and so on. Not all of the output, but what's in flight, right? So, and about service, the forecasting box is deployable as a service. In fact, there is already a pre-agreement with our colleagues in ESA that on the second part of this year, we should sit down and start working together to bring the forecasting box to the DESP, to the service platform of DestinE. Okay, so we actually already have it deployed as a internal service we can play with to find bugs and so on at ECMWF, and we will do so for the service platform also. And yes, it can be deployed as a service.
Thank you. Thank you, Tiago. Any other question from the audience? If none, then I have one with two branches. First of all, let me say that I really like the analogy between the data growth rate and the bank accounts. I think many people did. But also, I mean, in this journey, when you started the whole thing in DestinE, so applying this end-to-end AI stack in this context, which, let's say, development really made a difference to you? What is the one example that you could use in order to demonstrate how far we can go from your experience in applying this whole stack in DestinE Earth? And then the second branch, are you ready and flexible enough to adapt the stack to whatever will come from the AI factories? So
right, very good question. So I think DestinE Earth was groundbreaking enough when it started. So important to understand, when we started DestinE Earth, we didn't know that this AI revolution was going to happen, right? No clue. We were physical models and that's it. But we are going to scale them to a scale we've never seen before. But because we did that, we did the homework to say, okay, I remember that one of the first slides we did for DestinE Earth to say, we need to handle 1 petabyte a day of data. Right? We were prepared. We knew that we needed to build a stack that was going to be able to take over this torrent of data and be able to serve it, prepare it, process it, give it to the users. So in a certain sense, we were lucky enough that because we were ambitious, we did the homework to prepare that when the AI revolution came, okay, there's this big jump in capability, which surprised us all. But in a certain sense, from the point of view of the software stack and the pipelines and the workflows, we were like, okay, well, I think we can handle it. And of course, with a lot of work with our colleagues, and we needed to tweak some things, but I think the vision of DestinE made Europe ready for it. And your second question was in AI factories. In fact, because AI factories are basically an extension of an HPC, and I say is that it was a really smart choice that to collocate the first AI factories with the HPC, the European HPCs, because these are the people who know how to build them, right? And I'm talking about Sergey and Mare Nostrum and Lumi, and Pekka and Lumi and so on. These people really know how to build these machines, right? And placing them there. Now, at least we, the people who are used to work with HPCs, we can now do the next step, the bridge, and bring and port all these pipelines to the AI factories. They are ready to go there. and I don't see a huge demand. I think the more difficult, the challenge will be more, because we want, and you want, the open AI factories for a set of users we have probably never worked with. The challenge will be more on the link to those users, those usages we never saw yet. I think we'll need to do better there, but let's say the piping and all the infrastructure, the software infrastructure is already, I think, well placed.
Okay. Many thanks, Tiago. I think it makes a lot of sense. And please, guys, a round of applause also for Tiago before we move to the next speaker. Okay, many thanks. So in this discussion, we will move from the more high level down to the more technical, and then back again to the high level EU policies and initiatives. So next step will be now to go a bit deeper in terms of the technical insights that we can get. And for that, I would like to invite the next speaker, who is Jerzy Bojanowski, who is the Director of Earth Observation, Data Science and Products in Cloudflare, and he will speak about, that's very interesting, how we can refine Earth observation via embeddings, which could become the next data layer. Please, the floor is yours, Jerzy.
Thank you very much. Will this work for me? Yes, okay. Okay, yes, thank you very much. So, yeah, I'm going to talk also about the revolution. Maybe it's not so evident as mentioned just before with the weather forecasting coming from the physical-based models to AI models. But I guess this will also change a lot how we work with the satellite data. So I will talk about the embeddings. A few words, why I'm here. So Cloudflare is operating a big Earth observation data repository for the Copernicus data space ecosystem. I will not impress you with the numbers because we are not yet at the exabyte scale, but we are on the hundreds of petabytes of data. And we do also operate the data bridges, which is also important part of the destination Earth. So the way you bring the data to the HPC from these repositories. So Cloudflare has this, I think, quite big role in these two projects, European projects. So, sorry, I don't know if it's a delay or it's just not, okay. So yeah, so why we'll talk about the embedding. So I wanted to start with like challenges that remote sensing experienced since decades. They are like really decades long, probably like since the 80s or 90s, and still valid. So of course they are not all, but they are the ones I think they can be solved by the introducing of embeddings. So first of all, of course, the challenge is the gaps in the data we use from the satellite observations for many reasons, like from clouds for the optical data, but just irregular acquisitions because of the satellite systems. So there was a need to correct the data, to do the temporal composites and many ways to tackle this problem. But still, it's not this like a seamless data you work with. The second challenge was with the radar data, which is of course great because you can acquire data in all weather conditions, but it's not so intuitive for processing because it's not, well understood by the visual interpretation. So it's more demanding than optical data. And the other challenge is that no single sensor will actually give you the optimal setting of the data you need. Like you always need some trade-offs between the spatial resolution, temporal resolution, spectral resolution. And because of that, we know for years that the data fusion it's the way to go, but that's quite demanding, and there is like a lot of manual engineering required if you want to fuse data from different sensors, from different techniques like optimal and SAR, from different resolutions, and that's still a challenge. Going further, of course, if you want to use some supervised learning, you need a lot of reference data. Doesn't matter if you want to classify, you want to identify some objects, you want to do some modeling of physical variables or something, you need this labeled scenes or the reference data. This is maybe not for decades, it's a bit a newer problem, but just too much data that you have petabytes of data on the pixel level, and it's not easy to turn them into analysis-ready data, and even more difficult to the decision-ready data. And the other challenge that the transferability of the models you build on one data set, on one location, is very difficult to scale. So, yes, and last but not least, I think some of these challenges, when they are tackled, like for the data fusion, for example, it's often that they are algorithms made for certain tasks, and they are not so much reused in other projects, in other topics. So there is a lot of repetition of building the algorithms for the same tasks. And I'm not saying that the embeddings will solve all these problems, but they, I think, address many of them. So in the simple words, what we can do with these new AI models, foundation models for Earth observation data, is that we can turn the spatial data through the model into a very simple vector numerical representation. But with this spatial data, it can be a lot of different setups. You know, you can calculate the embedding on the pixel level. You can calculate the embedding for the parts of the image. You can calculate the embeddings for the whole scene. And depending on for what task you want to use the embeddings, so then you have to have a lot of settings, a lot of parameters to be defined. You can use a single modality, meaning one sensor data, one type of data. But you can also fuse many data sources to create the embedding, so that you have the information embedding. This embedding comes from the different types of data, and can be satellite, but can be metadata, can be thematic layers, many things. You can run the model that you have the embeddings only from the vision only, but you can also have the embeddings from the vision and text. So then if you have a vision and text, you can use a natural language to actually work with this vision information, imagery information. Further, then you can decide if you want to use the single resolution data as an input to the AI model, or you would use different resolutions. So then you can also have the information. Of course, different resolutions, as I said, of these trade-offs. I mean, with the higher resolution, you can have a different kind of information than the lower resolution, even in terms of spectral information and so on. And then you can calculate embedding for a single image, for the single date, but you can also have the stack of full year, calendar year, or the vegetation season, and you can calculate this vector representation only for this period. And of course, if you have the temporal stack, then you have a different information embed in the vector. So the advantage is that they are, I think, addressing some of this long-lasting challenges is that, first of all, you have the compressed information from this many dimensions, as I just said, temporal or different modalities or different resolutions. So you have them compressed into one vector. Then we go further just from radiance or reflectance, we go to the semantic meaning. So you can, if you have an embedding calculated from the whole season, you have the temporal variability also included. The information about this is included in the vector. Then, of course, the challenge of gaps, it's still there when you train the model and when you calculate the embeddings, but there are ways that you can really get the gap-free and consistent seamless data set of embeddings, which means that it's much easier and cheaper to run the machine learning models if you want to use the embeddings to derive some physical variables, or if you want to classify or identify some objects on satellite data. So that's the big difference. That the pre-processing needed before training the retrieval models, it's much lower. And also, if you have the embeddings calculated also for text. I mean, their capabilities for like easy in quotes, because there are of course some limitations, and I think it's a lot still to do. But you can do some image-to-image similarity searches, but also text-to-image similarity searches. I will show that as example in the next slides. Okay, but the point is that even if we are sure that the embeddings, it's the way we should transform the increasing amount of satellite observations, to do that, you need infrastructure, you need the data, and I would even say that data itself is starting to be as important as the access to the data itself. I mean, that's not, you can have a data but with not fast access as for the GPU needs, and then you cannot do the job. So this is the area we work in as a company. So I mean, we do our best to provide our users and clients the ways to consolidate the data from these different types of data, because only the homogenized ones can be used for the training. It's also related to the formats that we store the data and try to deliver. But there are maybe some aspects that are maybe less obvious. For example, the guarantee that the data is actually authentic, the one we use. And something which is also important in terms of training and using AI models is just surveilling the security of the cloud infrastructure we use. And the same for running the models. This will be more related to the language models. I will show you now. Yeah, so what we do operate is this more than 100 petabyte of Earth observation data. Most of this data is the Copernicus data space ecosystem. So the Copernicus data sentinels, Copernicus services, and so on. But what is important is this fast access to the data from the cloud. I guess the gap between the cloud and the HPC is also probably becoming a bit smaller, because there is also a lot of GPU capabilities in the cloud itself. So it's something to be discussed probably for training the models and huge runs. Of course, the HPC is the way to go, but probably for calculating the embeddings for the fresh data coming in, the Copernicus data space ecosystem, something that could be done directly on the cloud next to the data. And of course, the fast access to this data with the low latency is the key. About authenticity, this is the traceability service, which is available in the Copernicus data space ecosystem. And well, that's an important part, because that's the way you can actually see that the data you are using for training is the real one, and it's based on the checksums of each individual file in the system that you can cross-check in the traceability database. Well, I put there the EO embeddings there as well, because since the embeddings are something you cannot, visual interpretation is not possible, because it's only understandable for the AI models, then this authenticity is even more important, because it's not that you look at the image and you can say like, okay, it looks weird, like you can say, for example, for optical data. So that's also crucial to be sure that if we want to build some downstream applications based on certain embeddings, we need to make it in a way that we are sure that we are actually working on the authentic data. When we integrate the large language models into this field, and that's of course a lot of work going on with like chatbots talking to the EO data, either for just querying the catalog, but also to take some information. So our reply to that is like zero log, fully private capabilities of running a long list of LLMs in our infrastructure, so that you can be sure that it's fully secure for development of our applications. And coming to more practical, so for the training the models, So what we do provide, we try to collect, not all, but the major data set that are used for training of the GeoAI models. Some of these data sets are already available, some are on the roadmap, and they should be available very, very soon. Because I mean, we assume that the easy access to this kind of data sets is crucial for the community actually to explore the still quite new technology. And I think it's even more important for the embeddings themselves. So we did publish a global set of embeddings on HaDEA, so they are now also available on the Copernicus data space ecosystem. And this was before the Google model, before the Cambridge model from Tessera. The point is that this was not the pixel-based embeddings, but the embeddings calculated for parts of images, so for different applications, maybe not for the pixel level applications, but more for querying with the similarity searchers and this kind of things. And what we believe is that it's even more that the previous list of data sets for training, that the embeddings are required for the community to actually give the feedback that we can make some governance decisions on what kind of foundation models and which embeddings should become, for example, a standard for Copernicus. I think that's the big questions which is still valid. But you can come to HaDEA or Copernicus data space ecosystem and start working with the embeddings, and the list of them will also grow. And how many time do I have? 2 minutes? 1 minute? Maximum. 30 seconds, okay. No, so I want to show you some examples very quickly of how we use the embedding. So this is this text-to-image similarity search that you can ask with the natural language, and you can get in response the images of what you ask for. You can do this reference, image-to-image inference, so you can look for the similar images in your repository based on the reference image, based on the embeddings. And we also, 30 seconds passed, and now it's gone. Okay, now, so, sorry. And the other aspect we really heavily explore is the anomaly detection using embeddings from the Copernicus data. The point is that, of course, it's a known thing in remote sensing, but the point is that the legacy way would require from you basically to know what kind of anomalies, what kind of extreme events you are looking for. And the anomaly detection based on embeddings, the idea is that we actually look for whatever which is unexpected by the model. And so we calculate the embedding on the freshly acquired Copernicus data and compare it with the time series of the embeddings. So you can see that you can detect the updraft changes like wildfires. That's more dual use because it's the Russian. It's in Russia, the fire. But also like a permanent changes. That this is the case of the bridge built on the border of Russia and North Korea, but also the environmental changes ongoing, like a drying of the reservoir. And yeah, so that's my key takeaways. So first of all, that the embeddings can turn the petabytes of satellite data into analysis-ready features understandable by the AI models. But still, we think that the infrastructure is essential for the model training and the operational embedding generation, which will become probably very soon a standard as the next level of the Copernicus data. And that if you have this embeddings pre-computed on the global scale, you can start doing global scale analysis really fast, and it's much easier than it's now. And what we show is that based on embeddings, for example, for this anomaly detection, that there is quite big benefits for sectors like civil security or even the dual use. And what it was a challenge I mentioned at the beginning is that based on embeddings, you can power many applications, so you can reuse this product in many probably tasks and projects, which was not the case for the fusion of the different sources before. And with this, thank you for your attention and sorry for being a bit late.
Thank you, Jens. And I liked also the first key takeaway that you can go from petabytes of raw data down to AI data. It's really powerful. Any questions for Jens from the audience here or online from Slido, if any? Now is your chance. Feel free to use the Slido, guys, because there are many questions that I think will pop up also during the discussion. So Slido, the QR, I think it's available, so you can use it easily.
Okay, so from Slido, we have a few questions, especially on this talk. So the first one, interface. Oh yes, because people discover that they can also vote for upscaling some questions on the. So the preferred one, embeddings look like good old features, and thus are creating a bottleneck between the wealth of data and the diversity of applications. How do you ensure one can use generic embeddings for every specific application?
Yeah, so it's a very good question. I believe that we will have probably the global scale pre-computed embeddings for the chosen foundation model, and that's the decision to be made, but it will always be a room for on-demand generation of the embeddings for certain applications because of a lot of settings you have, the parameters you have, as I showed in the graph, so the size of an embeddings and the temporal coverage and so on and so forth. So I guess probably both need to coexist, like the big data sets already calculated, but on-demand processing will last. I guess.
Thanks. And we'll go to the other one, which is even more technical. In the context of Earth observation using vector embeddings, which AI model architectures, like transformers, Mamba, and training modalities are the most promising?
I think I'm not sure if the community is really able to answer this question yet, because my perspective is that because it's so computing demanding the computations, like the generation of the training of the models and generation of the embeddings, that I think there is still a lot of research that needs to be done to answer. I mean, I guess there are many experts that probably have their opinions, but my view is that we first of all need to allow the community to actually work on that, to come with this really strong recommendations of the technique on the architecture. That's my view.
Thank you. And still from the Slido, I will, very practical question. First a comment. Global embeddings at 10 meters make all other raw EO data redundant and can truly revolutionize the EO field. So that was the positive comment on your work. And now the very practical question. When will CDSC make global embeddings available as open data to everyone?
Sorry, why or what?
When?
When? Well, this I cannot answer because it's upon the agreement with ESA or probably, and also the European Commission. So I think there is no decision yet which model to be used to generate the embeddings on the global scale. And again, the problem is that it's a big investment, so it would be good to have the final decision. But on the other hand, we know that it's also there will be many more models to come. But also to have these recommendations from the community and the user perspective, we need to start providing the embeddings first. So that's difficult, but I cannot say when. We do our best in CRODIAS, which is like a commercial part of the CDSC, to provide the embeddings from the models that are already on the market and seems to be promising and well adopted by the community. So I guess this year we will have some global embedding data sets on CRODIAS available. Thank you.
Guys, join me.
Thank you.
Many thanks, Jens. And as promised, we will again go from the deep dive on technical insights to a more high-level now topic, which has to do with what you heard many times, both in the morning and also now, the so-called AI factories. So what we are preparing there, AI factories, AI gigafactories. So next speaker is a colleague, is a brother in arms. So Juan Pellegrin from DG CNECT, the head of the AI factories and HPC sector. And Juan is going to talk to us exactly about that. So what we are currently planning to do with the factories and what is the Commission AI innovation package. So Juan, please, the floor is yours.
So, good afternoon to everybody. So, thank you for the kind invite and the nice presentation. Okay, the idea is to give you a flavor of what we're trying to do, in particular in the deployment of infrastructure in Europe, and to clarify also on different concepts that have been mentioned this morning. I will go to the point. Works. Next slide, please. Okay, so just for those that you do not know, all the HPC strategy in Europe is deployed by the joint undertaking. This started already in 2016-15 with a declaration in Rome. Only 6 countries joined then. Today we have 37 countries around the table and many other countries knocking on our doors because they want to join their HPC. Okay? We do many different missions, deployment, research, skills, etc. So why do I put that slide? Because if I want one takeaway from my intervention today is that everybody today or tomorrow, you go to their HPC website with all the resources that they have at their disposal for you. Okay, I would be pleased if that would be the case. Next slide, please. So this is the status of the deployment of infrastructure in Europe. As you can see, we are really deploying a wide and ample and geographically the supercomputing network in Europe. Okay, and this is going to be enlarged. This is the status as of today. The latest system was Jupiter, that was already accepted last September. I can tell you already that the upgrade of Leonardo in Italy is about to take place. The system in Sweden is almost there, equally so for the Greeks. So gradually, we're really deploying the infrastructure, which is, the idea is that we provide compute to our stakeholders. Our stakeholders, including Destination Earth and including other services, they are insatiable for compute. No matter what we offer, it's never enough. In particular, in today's world of AI, nobody is happy. Okay? The idea here is that we grow the cake of compute, and we're really committed to that. Okay? So I think we've done a nice job. This is, we are really deploying state-of-the-art hardware and software, and I will go next to the factories. So this is a great job of the JG, I have to say. So the joint undertaking has really done a marvelous job in trying. It's not easy. All of you that are embarked on procurement processes, it's not easy to launch a procurement and get the systems ready and make them operational. Next slide, please. This is the status. The slides will be there. So where's the political framework? Is the AI content plan. This was presented this morning by my colleague, if I understand well. So I won't go into further details. Basically, that my angle is basically the computing infrastructure, and it links to the different other elements that were mentioned this morning. Okay? Of course, the apply AI strategy, the data spaces, we'll come into that later. And then the new kid on the block, and I'll give you a framework there, is on the AI gigafactories. Everybody likes mentioning them. I will try to explain and give a flavor of what they are and what they are not. Okay? So just to be very clear, very much support from our political masters. It's a critical element for our European sovereignty. It will really make a big change in Europe in terms of the infrastructure deployment, and we're approaching from a different angle to that of the HPC. I will explain that later. Next slide, please. So, to those of you who have been working with us for lately, Just to recall that the AI factories, from a legislative point of view, was launched only in January 2024. In such a quick time frame, we have managed to get, that was the legal text, we have managed to select and start deploying 19 AI factories in Europe and 13 antennas. Believe me when I tell you this is a miracle to Commission standards. Just to be very clear. This will include, because we have member states behind us. So we presented the initiative, and suddenly we started with 8 systems, and suddenly almost all member states and associated countries wanted a factory or an antenna. They were bewildered by the concept, they believed it was necessary, and they put the money behind us. Okay? This is a real success, to be very frank with you. These 19 AI factories will multiply by a factor of 5 the AI computing capacity in Europe. Okay? So be patient for those of you that are constantly claiming for compute. And I know I'm looking at my friend Baris in this context. Okay? So 50 new AI supercomputers will be in the process of being procured. Okay? So these are the key elements, and we'll go later on. And we have mobilized around 2.6 billion in 18 months. This is a real, in the current context, from a budgetary perspective, member states and the EU have tried to look deep into their pockets to look for this money. This is a fundamental element contributing to our sovereignty. We need to make sure that the data, the solutions that we develop take place in Europe, in European soil, and the European conditions. This is fundamentally critical. Okay? Next slide, please. So what are factories? I'll go to the next one because it's easier to explain. AI factories, as mentioned by Tiago this afternoon, sorry, is built around the supercomputers, and that is the core of an AI factory. But around that factory, we have introduced all the necessary elements to make AI flourish. Which are those? Of course, data. The factories have a task to look for data, make data available. They need to link with the data spaces. They need to facilitate the opening of data for our users. All the necessary support activities. AI factories is not about compute, which is necessary, but the talent we have in those HPC centers is massive to help our stakeholders to develop, to improve the way they develop their AI solutions. They have the algorithmic programming facilities, they're willing to inference activities, the cloud, etc. So all the necessary elements are around the HPC centers, the AI factories, so that any user can go there and ask for support from A to Z. Okay? This is the message I want to pass to you. Go and give them a bad time. That's what they are for. They will provide you with all the necessary help. And if they don't, you come back to me. Okay? We are putting a lot of money to really enhance the AI ecosystem in Europe. That's what the factories are for. It's not only compute. It's all the necessary support services around that. Okay? I leave it there. Next slide, please. And this is one of the 2 slides I really want you to remember. And please take as a task for tomorrow. Go to the HPC website. You're just 1 click away from those services. Compute, talent, training, programming support, algorithm support, you name it. So 1 click away. Okay? They will guide you through the different networks to the right person, depending on the domain you want to particularly this one. They know where expertise is. Okay? You are one of the specific disciplines that many of the factories are focusing on. All the talent, all the expertise is there. If they don't have it in your specific AI factory, they will channel you. They will tell you where you have to go. Okay? That is the role of the factories. We do not want to duplicate 19 factories, all of them doing the same. Each one of them is specialized, specific domains, specific activities. Okay? Remember, 1 click away. Next one, please. Equally so for the access. We have fine-tuned our access policy when we launched the AI factories. We have enabled a so-called AI factories track to complement the activities of HPC. We have really streamlined the process. Indeed, for all the HPC domains, It remains very competitive, and the scientific disciplines, they require a lot of compute, and the process is there, and it's very competitive. That remains. But for the AI factories, for all the AI services, we have really streamlined the process. I know who was speaking about access to GPUs, I think it was you. We have enabled a track, it's called Playground Industrialization. In 48 hours, a small person, an SME, will get access to GPU. That's the track, that's the idea, that we facilitate the uptake of HPC infrastructures in Europe. We have really streamlined the process. So please, have a look at it, go to our website, there are a lot of calls, there are lots of opportunities, so please, I really encourage you that you have a look at this, because really we are really facilitating and we're really encouraging the uptake of compute through the AI factories. Okay? Next one, please. So, the next new kid on the block, AI gigafactories. Increasingly all over the press, all over political, and many statements around the Commission and elsewhere on the gigafactories. Just to preempt any question on when the call will be launched, the quick answer is soon. I don't want to be committed to any specific date, but we're almost there. We're really working with member states, so that our real idea is that we launch this soon. Okay? We do understand that the need for compute is there. So that's the idea. Okay, so basically a gigafactory is much more than we rely on the concept of a factory, but we multiply by 4. So the dimensions, the capabilities of the gigafactory will be massive compute made available to European stakeholders. Okay? The idea basically is to really provide the compute necessary to train AI frontier models and those beyond that. Okay? We are targeting the selection of several gigafactories in Europe. The cost that we anticipate at this stage is between 4 or 5 billion euros per gigafactory. And we have the idea of the commitment that we'll be mobilizing will be around 20 billion in Europe. Okay? A fundamental element that needs to be understood. The gigafactories, contrary to a factory, it's privately led. So the bidders that will respond to a gigafactory will be private consortia. Okay? The role of the public sector is largely to the risk their contributions, their initiatives. We will buy compute from the selected gigafactories, both member states and the union through the Commission. Okay? As said before, we plan the call in spring, so very, very shortly. And again, this is a fundamental element for our sovereignty. We really want that the models, the data remains in Europe when we deploy these gigafactories. Next slide, please. And then finally, I think given that the community here is very much destination related, I think there's an important role for these stakeholders to work with AI factories and later on with gigafactories. You are an important, or I would call it, primus inter pares domain. You love it very well to get strategic access from the HPC resources. So all the services that are currently being offered by the factories, by the HPC systems, are also available to this community. So please go again to whatever factory, to HPC supercomputer, to ask for compute and all the necessary support services that you may wish. I think this ought to do with the data that is available. They will really facilitate an A to Z, end-to-end journey when you go into a supercomputing center. I think similarly, I think this ought to do in terms of capacity building, in terms of training. We have a lot of expertise here in HPC systems, so I think we can do much better when working with AI factories, etc. And it's a core activity, by the way, of the factories. And then I think we have the necessary talent. We will be getting additional compute in order to accelerate the digital twin transition in Europe with you. So I leave it there, Babis. Okay, and I'm happy to take any questions. Thank you.
Thank you, Juan, and thank you for being very efficient in terms of timing. Still, the chocolates are a challenge, but we will see. I think it's quite important if you can just clarify for the audience, what is really the main difference between the factories and the gigafactories? So what are the challenges that each one of the factories, categories of factories, if you like, should address? Which communities, for example, what are the differences? Because I think that's quite important to stress it, to highlight, so that you know, the people also watching us online, they can understand where they should go, with whom they should engage with.
Okay, thank you for the question. The main difference between, at this stage, is AI factories is a public research infrastructure. So the idea is that all our communities, scientific communities, and in particular SMEs, small SMEs, go through the AI factories. Access, I forgot to say, to these supercomputers is free. Okay? This is a fundamental element. So today's the AI factory with the most computing capacity is Jülich, with 24,000 GPUs. A gigafactory will have at least 100,000 GPUs. And we do know, because we had a call for expression of interest already launched last summer, that the interest behind this initiative is much more than 100,000 GPUs. We really want to deploy massive compute capacity in Europe. Okay? So the activities that need to be undertaken in a gigafactory are beyond what can be achieved in a factory. Okay? I will leave it there. Yeah. And then the other element is that a gigafactory is privately led. So even if we are buying compute from them, they will have to be sustainable in the long term. The business model has to make sense. They are mobilizing 5 billion euros. They have to go to the banks. They have to make the business model. So they need to know how to make money, also with EU and member states when buying compute, but they need to make their case, what services they're going to offer, etc., etc. Whereas the factories is very much HPC-centered, as a bit of the advance, a new change of paradigm from the HPC previous scenario, but it's a publicly funded research. So I think it's a bit different. That what needs to be targeted when going to a factory is big compute, big models, big training, whereas except for Jülich, the rest of the activities are of a or smaller scale.
All right, many thanks, Juan. Now, let's see, any questions from the audience for Juan? Or from Slido, perhaps?
So from Slido, as we just previously learned from the ECMWF presentation, data for ML pipelines must be located close to the GPUs. With distributed AI factories, do we have the need to have copies of that data in every AI factory?
Maybe I can try to answer if you don't mind.
One thing that was not so explicit in my presentation, but Matt mentioned this morning. No, we don't need to have copies, because when you prepare the data for your training, you shape the data for the particular training you're going to do. Because every training model or training framework needs the data slightly different way. So you need to move the data, and as you move it, you shape it, and you make it the shape it you need for that training.
Thanks.
There's also a question from the audience. Andrea?
There's a question up here, actually, first.
Okay, then we'll take this one.
Hello, I work in the space data economy, space economy unit in DEFIS. I had a question which is more like a curiosity, because I saw the map of AI factories and I never understood what actually generated and how is this specialization expressed in the different AI factories. Like, why is one specialized in space and what does it mean? And the second question was, when you have AI factories that don't seem to be connected to the HPC capabilities, are those different, or how are they thought? Thank you.
Thank you very much for your question. Indeed, when we launched the AI Factories call, we requested those countries willing to host an AI factory to identify those domains that they would like to pursue. Not all factories have expertise on all the domains. They need to address their national ecosystem. So how are they going to respond with these new services, this new compute? How do they could enhance the national AI ecosystem? So they had to identify those domains that they would like to pursue. So each country has decided which ones they want to target. Indeed, there are many overlaps. So for example, if I recall well, the area of space is followed by 3 or 4, but for example, the area of health is all monitored or targeted by almost all. So what are we doing? We are launching now, soon we're going to be launching a so-called AI Factories networking call in order to enhance the collaboration and work between the different AI factories. Okay? We have to avoid duplication of effort and maximize the resources so that we do not pay 2 times for the same thing. This is in the making, and we hope that this is launched very soon. The second question was on... sorry, yes. I didn't want to go into detail. These are the so-called AI factories antennas. So an antenna is a site that provides the necessary support services in terms of training, algorithm support, application optimization, etc., working with data, but they do not have the compute. They are associated with an AI factory that has the compute. So, for example, the one in Cyprus is linked, the Cyprus antenna is linked to the factory in Greece, and alike, okay? So all the antennas, they provide the services, but they do not have the compute on site. They have cloud-based access to the compute provided by the AI factories. Sorry? Text?
Tech support. Technical support.
It's all the services. It's all the services I presented in my slide. So they have to really identify so they have to have the competence nationally to provide services to the national ecosystem. The only thing that they do not have is the compute. That's the only difference. Fine.
Andrea Taramelli, the National Copernicus Delegate, Italian National Copernicus Delegate. As we are always underlying, as far as we understood, the EURAC HPC is not operational in terms of services. So if I have, a request from the National Civil Protection, in terms of also Destination Earth, it's based on a quote. Maybe it's not available. So what are the planning to make the EURA HPC an infrastructure that is operating H24 for operational services, if there's a plan? Otherwise, like in Italy, we had to invest quite a lot, not only in Bologna, in other cities like Rome or Naples, to put around the Leonardo HPC of CNECT what are the operational services to deliver to the Met Office or to the National Civil Protection.
Thank you for your question. Indeed, I think there's a willingness from our hierarchy and from the factories to really deploy operational services 24/7. The resistance we get is very simple. Please pay for it. So this is basically what we get from the different HPC centers. We are trying to push, and we will push to our HPC AI factories to try to start providing the services. And we know that in the current AI revolution, we cannot work 9 to 5. That's obvious. So we take this as a homework, and we'll try to pursue that this is enabled, amongst other things, in terms of how the queuing is organized, etc., in terms of AI. But yes, your point is well noted. We are aware of it. And we'll try to pursue this with the factories. Thank you.
Okay, many thanks, Juan. If we have other questions in Slido, let's hold them because we are running out of time because we started a bit late.
The last one, please.
Okay, last one, and then we move to because we have 2 more panelists that they would like to join also to have the open discussion.
George Gomes from Virtual Operations Support Teams in Europe. My question comes with, we're doing all of these investments, but will data come with it? I'm going to give you a very small example. In 2023, together with the JRC, we trained a model to detect requests for help during catastrophes on Twitter. And we used that on the aftermath of the Turkey earthquake. We were able to detect 40 requests for help where no one was there, and they went there and saved 21 lives. Now, when the storms happened in Portugal, we didn't have access to the data because there's no longer access at the GRC to the Twitter API because it costs a fortune. DJ Connect, you know that the DSA is implemented. We still don't have access to social media data as platforms are obliged to give us. So will that come with data as well, or do we have still to wait to access data to train models that actually can save lives? Thank you.
Indeed, you bring up an issue that is fundamental for the optimization of our systems, the access to state-of-the-art and timely data. Indeed, the factories have a task also to improve data availability, data discoverability within the mandate. I don't want to go into more details about the so-called data labs that we're going to start deploying on the factories, but indeed, this is an issue we have identified, and we'll try to pursue how we can really facilitate and widen the access to data in Europe. And again, indeed, we have also many HPC centers, the urgent computing approach, that way they need to really react fast, as you signal to HPC, this is I always say, saves lives. We have to make sure that this materializes. We have very good examples. I think much more can be done. And in this, if data is the key element, we need to strive how we can really encourage the different players to open up data. Yes.
I think if I can also compliment Juan in this reply, the plan is that we interconnect all the factories with our common European data spaces. So the whole ecosystem, all the verticals, from agri to energy to health. And then we have, of course, initiatives like Destination Earth, like the Open Science Cloud, that we will make directly available the data assets, for example, of Destination Earth to the factories. And then more will come with synergies with Copernicus, and so on and so forth. So the data ecosystem will be there. That's the target. So that we bring, as we said in the beginning of the session, the two major elements, the data that we need and the compute power that we need. So there are plenty of actions, also how all of these are going to interconnect. So in the break, we can discuss also about how this ecosystem will really come into place. So again, many thanks, Juan. Please take your seat. Give a round of applause to Juan. And now let me also invite also the last two speakers to take part in our panel. So Miruna Stoicescu, who works as the lead in AI for digital solutions in EUMETSAT, and Luca Girardo, who is the Destination Earth and Copernicus Advanced Infrastructure Service Manager in the European Space Agency. Please take a seat. Like a good moderator that I am, I did my homework. I have already questions for you guys also, but also for the audience, please, while we are discussing now, prepare your questions in Slido so that we can also try to answer them, although, again, we are running a bit late, but I think the discussion is quite important to have. So let me take my mic. All right. So, of course, allow me to give the floor first to the two ones, Miruna and Luca, that didn't have the chance to speak. And there are my notes. So, Miruna, we discussed a lot on how we can really prepare AI-ready data sets. So, since you are working in this area in EUMETSAT, in what ways AI is being integrated into the EUMETSAT operations so that you can enhance the capabilities of Destination Earth, and then in turn, how this could possibly feed into the Copernicus ecosystem? So, there are also mics there, but...
So, hi, thank you very much for your question, Bobby. So in EUMETSAT, in general, in EUMETSAT, we are looking into how to apply AI in different areas. So for example, predicting system failures or identifying outliers in satellite telemetry and so on. In the particular context of Destination Earth data lake, so the component that EUMETSAT is operating, We use AI to help users navigate in our system. So we have a chatbot, an AI assistant on our DestinE Data Lake web portal that helps users learn how to use the APIs, explore the data sets, and so on. This is also the case for Wikio, so the platform, the Copernicus platform that is also operated by EUMETSAT. So there's also a chatbot, and there's this notion of supporting users in onboarding basically on the platform. In the DestinE Data Lake, we also use AI for enhancing certain data products. So for spatial and temporal super resolution, we are experimenting with this. And more importantly, I would say we aim to support users to develop their own applications. So by giving them environments and tools that help them develop their applications next to the data. So this is what we call the near data processing, or the paradigm of bringing the users to the data. So in DestinE Data Lake, that is a distributed system. Tiago was mentioning the data bridges, so we have the multiple sites, and on all these sites that are next to large data holdings, there are also processing capabilities for the users to do their own developments, basically.
And then to address these challenges related to the large data volumes and to the processing efficiency that you need to have in these codecs, would, for example, what Jens was presenting, bendings, could that be helpful? Are you already experimenting with that?
Yes, that's actually a topic that we are very interested in currently, and we are also exploring, well, together with him as well, because they are the main service provider on our DestinE Data Lake, yes, that's true.
Jens, this is now the ball to you, but we will come to it later on. So then let me go to Luca. Luca, in the infrastructure that we have in Destination Earth, of course, there is immense cloud data repositories, but we have also the massive compute power from the EuroHPC centers, and now the upcoming factories. So how you would be an architecture that will seamlessly bridge both? So the data, the cloud native part, if you like, together with the high performance compute power. And is this something that you've been already working with in the context of ESA collaboration with Destination Earth?
So thank you for the question. It's a very interesting question. So, well, we have some ideas, and we are also working on these elements. We believe that bringing all these elements together in a seamless way for the users is a key. And enabling that for the users, we also need to enable for the whole system at all. So orchestration for us between cloud resources, commercial resources, EuroHPC centers, HPC center, commercial one, is a key element that we are really scouting. We have a project inside DestinE, Hippo Code, that is really trying to find the best solutions that enable this orchestration in terms of how we can take advantage across the full chain. We know there are initiatives like Simple and Federation Platform we take advantage of. So it means that it's already activities are going on that element. What we want to understand on our side is also how we can make advantage of them in the full chain of all these services. But clearly being able to, let's say, stream workflows across different infrastructure is one element. Then you will need the data. And the data we have understood is big and massive. And clearly we cannot afford to now to bring not 85 petabytes, not exabytes and of data to the users. But we are learning that the AI is changing a bit the paradigm. Training data sets do not need to be super huge. They need to be very representative and have good quality. And that has been on our side understood that we are now at a certain moment where we can move towards bringing these assets in operation. So in terms of creating these assets so that user can take advantage of, we have also launched an intended call on either side for the Earth observation hypersphere, where we start building these assets from training data sets on Copernicus data, benchmarking. We have understood that that is also another element. So having all these different elements that talk to each other, having, let's say, the infrastructure that allows you to operate a different type of infrastructure in a seamless way, is all the elements that for us is key to really come to industrial services. And somebody was speaking about operation. Yes, that is the next element. So you have to build up on top of that an operational service, industrial operational service. And there are key elements that we cannot, let's say, hide. So we need to availability of this infrastructure. We need to ensure that also performance of that infrastructure. Now, orchestration allows us to hide a bit of these different elements because we can build on top of different HPC center, different cloud providers and so on. But yeah, so we are gathering really the experience required then to ensure that we have an uptake by industry to offer this type of services, because at the end, that is the key element, that the industry is capable of provide us these services to us, but also to European customers and probably worldwide customers, so that it becomes a commercial viable solution.
Thank you, Luca. This really now gives me the chance to pass the ball to Jense, because you were talking about the role of the industry. And then, Jense, where do you see now, how you will position the role of the private sector in this context? So where do you see opportunities? Where do you see challenges? You heard both Miruna and Luca referring to it. Perhaps it's a new area, perhaps it comes with inertia. So what do you think about it?
Well, that's a quite complex question, I would say. And depends on what the perspective I would tackle it now. So first of all, I think okay, it's true that for the AI development training models, the HPC, the AI factories, gigafactories is the key. But still, there is a need for the data to be brought to this infrastructure. So this is what we do with these data bridges, mainly at the moment for the Destination Earth Data Lake project. For the embeddings, the question is that from the commercial point of view, providing the embeddings on the global scale from various models is very difficult to be justified, just really commercially. So I think it will be healthy that the two systems coexist, like the public one that will provide the global embeddings for benchmarking, for testing, for a global scale compute of the, I don't know, like Copernicus products of this kind of things. But still, the commercial sector needs to provide the tools for the on-demand processing. It's not that one fits all will work for the all tasks we need to tackle. And then maybe the last point is that, of course, I mean, to what we provide, we required also a huge infrastructure, and this is very difficult to be built without also public investments. And what we try to do is that we build this infrastructure really fully European, based on open source data, like to really provide Europe the sovereign solutions in this aspect for the cloud computing. But as I said, I mean, without the public support, that's very difficult with like long-term projects and vision. So that's my view.
Thank you, Jense. This is very clear. That, Juan, if I turn to you now, because there's a call for support from the public sector, as you heard. So what you would reply now?
In terms of infrastructure, to be very frank, until the new MFF is around, we have depleted our funds with the 19 AI factories, just to be very clear, and the gigafactories. I do think there's a wider opportunity more in the supporting of the development of a European software stack. I think that's an area that we need to start considering also supporting at different levels. I think we really need to look into that. It's not easy. We really need to, what's happening in the markets today with major players buying all the different open source companies, for example, Slurm and others. So basically we are faced with a lock-in effect. So I think at some stage we really need to focus, and the support I think should be coming from our side. Now focusing a bit more also on software developments. We have some initiatives already ongoing on hardware. So I don't want to go into detail, but we have the RISC-V initiatives that we are pursuing. There are different companies that are beginning to scale in Europe. It takes time, so we have not neglected that. We are working with the CHIPS EU also to trying to develop a bit our sovereignty. It takes time and money. So really I have to convince member states that it's worthwhile investing on sovereignty rather than increasing the stock price of different American companies. So we are pursuing that. Let's be very frank, it's not easy. Developing chips is a very complicated endeavor. There's another American company that they have failed their technological roadmaps in the last 6 years, for example. So it's a trial and error effort until we make it there. But I think some breakthroughs are coming up. Last week or 2 weeks ago, we had a nice announcement by Accelera, for example, in the Netherlands, another SME in Spain with Semidynamics, really deploying chips at 3 to 2 nanometers developments. So we have the talented skills. I think we have to pursue that. That we should not throw in our towel. And I think that's the way we are really trying to support our sovereignty. In addition, to, for example, in the Gigafactory, etc., we really want that open source support our companies, the bidders. We really want that European suppliers also a part and parcel of the Gigafactories initiative. It's a sovereignty element. So we have not neglected that. On the contrary, we are promoting it. And for example, in the call text for the Gigafactories, the sovereignty element is strongly behind that.
Okay, many thanks. One, it's clear that there are a number of actions already in the pipeline, but more will come, of course, in the new MFF because it's a continuous strand of work. So we will not stop in 2027, 2028. The investments will continue also in the new MFF.
Certainly, certainly. So I cannot anticipate what's going to happen with in the new MFF. How would I do that? But the idea we have is that this is a long journey. We are at the middle of the marathon. Again, my message is here, we do have the skills, we have the commitment here. So I think once the compute becomes to be deployed, I think we have the right elements, and I'm pretty sure at some stage we'll make a breakthrough. And I think we're going to pursue that.
Thank you, Juan. Since we are coming close to the end, any questions from the audience? Or from Slido? Do we have?
So a question about, I try to summarize a few similar questions, but they all tackle sovereignty, and maybe more for you, Juan. So the global question is, how do we compete with US and China in the global competition, even also knowing that US is spending two times more than us, than Europe? And a sub-question would be, do you have some requirements on buying European chips or this kind of European-made products to fit in the factories?
To be very clear, I have earned the chocolate. I think the race is far from over. Indeed, we are competing with massive amounts of investments that are taking place in the US, in China, that we are not ready to equal. But I think the European approach, we need to focus exactly where we are good at. I think it's not just a question of deployment. We have the skills. I think all this compute that's being deployed does not necessarily come up with the necessary support, the skills to really make full use of that. So maybe it's a lot of bare metal that's been made available. I think our approach goes beyond that. So I think we have to target our investments and our services to really optimize fully and the infrastructure that we are employing. On sovereignty, last week, I believe there was a paper. There's been discussions on this by European discussions. Let's see how this develops. There are many considerations and discussions ongoing. But just to let you know, for example, in all activities, when we buy supercomputing infrastructures, or further so in the Gigafactories, we really strongly encourage that the proposals do incorporate European technology. No matter how small they are, we really encourage it. We look forward that these procurements must be seen as an instrument to really develop in European sovereignty, and we're pursuing that. Of course, I will be willing just to buy European chips if they existed, which are competitive. This is not the case today, let's be very frank. But we can provide that racks incorporate the European technology, that we work on them, that centers of excellence are deployed around the supercomputing centers, etc. So indeed, we are really trying to pursue that HPC, and it's becoming a very political element, brings in all the sovereignty elements, and we try to support the ecosystem that's behind the Europe.
Okay, many thanks, Juan. Unfortunately, we don't have enough time to also take more questions. Mark Dowell is coming after the coffee break with a very interesting session also on user needs and trustworthy AI. So please join me for a huge round of applause for our speakers and enjoy the rest of the workshop.
Okay, let's get started because we're already kind of 5 minutes into this session. Good afternoon, everyone. I realize the oxygen level in this room is probably going down a bit at this time, but hopefully, I also noticed, I don't know, Mitch is not here, I don't think, but I also noticed that the bag of chocolates is almost empty, so I hope he's got some, more for tomorrow, or else that plan will backfire. Okay, so this session, the last session of the first day, will address something that I think has kind of been in the background in all of the previous sessions. But if we think of our tagline for this meeting, from innovation to services, then in reality, the user needs, and how we ensure that we're delivering trustworthy AI solutions to those users is really a fundamental part of that. And I think, at least within the European Union programs, and in particular in Copernicus, that service delivery aspect and the link to the users is really key. And that has many different dimensions. First of all, of course, at that point, AI becomes a means to an end rather than the end in itself. It's about delivering fit-for-purpose services to the users. And what we see, or what we imagine and have seen already at some points during today, is that the AI provides a powerful tool to bridge gaps that still exist between concrete user needs and the services that are already available. The other thing it does is improve discoverability of products and services, and we're going to hear a bit about that. And then finally, of course, AI comes with it a lot of elements of responsibility as well, and thinking on how we ensure a trustworthy and ethical use of AI in delivering these services, I think, is fundamental. So the structure of this session is we're going to have a single presentation, actually from a colleague of mine working in the Knowledge Center for Earth Observation, specifically showing how we use AI methods as well in actually looking at the requirements themselves and needs that we're gathering, in our case, from the policy GEGs of the European Commission. And then we're going to have 2 sub-panels. All of the panelists are on stage at the moment, addressing these 2 aspects that I've just described. I should mention that this session was organized together with my colleague from DG CNECT, Bertrand Lesseau, who is there. So it brings both of those perspectives, as do all of the sessions, by the way, in this meeting, the perspective from Copernicus, in my case, through the Knowledge Center on Earth Observation, and Bertrand's perspectives coming from DG CNECT. So with that, I suggest we start straight away with my colleague, Miguel Vallejo Orti from the Joint Research Center. And Miguel is going to tell us a bit about using AI for prioritizing policy-driven Earth observation product requirements through the work we do at the KCO. Come on.
Thank you, Mark, and good afternoon, everybody. And thank you for letting me be here today. Yes, I will be basically talking about different tools and how we use AI to prioritize policy-driven Earth observation products within the Knowledge Center of Earth Observation. Okay. Yes. So what we do at the Knowledge Center of Earth Observation, the KCO, is basically trying to support policymakers in the full exploitation of Earth observation products and services for the implementation of European policies. For this, we work at different levels, first extracting the needs from the policies, translating them into technical requirements, and trying to fit for purpose products. Since there are not always products satisfying the policy needs, we also identify the gaps And the analysis of these gaps is actually very useful to direct research needs and also for prioritizing innovation within the European observation programs. That's what we call the last mile gaps. Okay, so one of the challenges we face at the KCEO is the massive amount of information and also the heterogeneity of this information, both in the policy side, but also in the product side. And that's where artificial intelligence actually plays a vital role and helps us a lot to extract patterns and to accelerate some of the pipelines. So trying to, explaining this in a bit simpler, but also concrete terms, we have on the left-hand side all the policy ecosystem in the raw policies, but also in a more digested way through reports and different surveys that we conduct between the KCEO and the DGs. And on the right-hand side, we have the products, the catalogs, and coming from different sensing platforms, and not always with the same metadata standard or with harmonized metadata. So the goal and the challenge is to actually connect these two universes in order to make the assessments. So we do the assessments to decide whether there is a match for a need in terms of a product, a partial match when a product exists but it needs improvement, or a no match at all. So in this pipeline, we find artificial intelligence quite useful in different dimensions, different points, different pillars, like the identification of the policy needs, in the harmonization of the metadata, in the data discovery, while we are searching for products, and in the final assessments, and the prioritization of the needs, of the actual needs. And these are basically the four main lines I'm going to cover throughout the presentation. In the first block, in the identification of the policy Earth observation needs, we do extensive exercise of data mining through the different policies and text mining to extract the targets, indicators, and Earth application needs and translate them into a tabular form, standardized in a way that it can be embedded and connected to a relational database, and actually connected to more complex and further assessments. In the block of harmonization of metadata, we start doing just putting or setting common grounds in terms of terminology, both in the ontologies of the thematic groups of the data, but also in the technical requirements of the data, of the product, sorry. So basically, we create common grounds, common terminology, and common semantics, which are going to be helpful and very crucial for the subsequent step of harmonizing the metadata. And that's what we do here. So sometimes we face different metadata sheets with a bit following different standards, and we translate them into very simple but very robust group of technical specifications, which are, again, under the glossary that I mentioned before, in order to facilitate this connection between the products and what the product can offer and what the policy needs. But while doing this exercise, it's actually very common that some of the fields are missing. So we use, again, machine learning to impute values using some very reliable training metadata sheets and to predict some of the missing fields, very importantly, maintaining a metadata score or a metadata confidence while we are producing new data coming from AI. In the next point, the next block, which is about product discovery, we are building taxonomical trees to basically facilitate the browsing of the data, the searching of the data, the discovery of the data, since we are dealing with massive and very big catalogs, and sometimes it's not that straightforward. But the question is, how are we going to build these trees? Because now we have many ingredients, like the thematic domains, but also some technical specifications, spatial resolution, etc. So if we build a tree and different hierarchies of the tree in a specific way, which is not very suitable for our purposes, we might find a tree, or we might find our products, the products that define the needs, not always together in the leaves, in the final leaves or the final branches of the tree. So what we want is to build trees which are adaptive to specific needs. So when we browse and then we look for them, they are together. And if they are not together, if they don't exist, because there is no such product satisfying that need, we can go one step upper within the same family and find the product in a neighboring branch. So the idea is we have an application need, a specific need from the policies. Like in this example, we are looking for products to do early warning of atmospheric outbreaks in cities. Obviously, we have to build a tree with the first hierarchical level on the thematic domain, so atmospheric products, and the second will be the temporal resolution, products with very high temporal resolution, because we are looking for early warning products. And then we'll see what we have. But the most important conditions are already set at the beginning of the tree. And then we can basically decide or assess which type of analysis can we do within this thematic domain. And this logic can actually be applied at individual need, or trying to look at the big picture and putting together many needs and tailor it or being adapted to a group of users, like it can be a DG. So this type of trees, as I said, can be dynamic, can be adapted to a specific need or a specific policy or a big group of users. In the last block of prioritizing Earth observation needs, basically, we assume that we have already done the assessments, like we did following this survey that we conducted between the key CEO and the different DGs, and we want to interpret the results, the different results. Again, we use artificial intelligence to mine those different forms, and first filtering the non-matches and partial matches that I defined at the very beginning, and do some using some LL models, we extract keywords to identify the topics of all the different clusters and try to direct topics by highest importance or highest occurrence. So what we did, basically, was selecting specific parts of the forms, extracting keywords, and assigning for each form a vector of information, and each of the elements of those vectors is a word with a value of the importance of this word or this term within the particular form. So now we can make the forms comparable, and as I said, each form is a vector of information, a vector of words, and now we can, using any clustering algorithm like k-means, to define the clusters. Yeah? And the results, after clustering around 200 forms, looks like this. So this information is very useful for us because now we can have a first impression of where the needs are. So in this case, we found the most represented cluster, both in terms of the size and the composition of the clusters. In this case, we found that the most represented clusters was land monitoring and changes. The second was in the domain of energy and the GHG emissions, and the third cluster was water quality and turbidity. So this is a start, yeah, to basically start directing research efforts, and this information, again, can feed or can inform the evolution of services and products, can also inform the in situ strategies, and can help to prioritize different prototyping activities. Another level of analysis will be to aggregate by DG, for example, to identify overlapping needs in terms of data, or by policy file to enhance simplification and just following the principle of measuring once and serving for multiple policies or multiple purposes. So just to wrap up and to finish, we prove, or we have used machine learning and artificial intelligence in many sense, and it reduced a lot of burden, a lot of manual work within our team. But for sure, it's required systematic verification of the different processes and the outcomes from artificial intelligence. But again, I think we really tackled the different points of increasing discoverability of the data, and the second point, very important, of how to manage uncertainty in the results, as we explained with this metadata score, for example. And we will also discuss here in this panel how to increase, or we discuss the opportunities of filling or breaching this last mile gap by integrating artificial intelligence in products and services. So thank you very much.
Thanks, Miguel. So, thank you very much, Miguel. As I said, that was really to show even in the kind of needs and requirement gathering and curation process, how we're starting to use AI and machine learning in some of the activities. So now we're moving on to the panel. As I said, this panel is split into two fundamental parts. The first is really addressing this aspect of that Miguel mentioned in his last bullet there on kind of how artificial intelligence has helped us to address some gaps between the core user needs at certain levels and the products that are available. And it's kind of following on a bit. We heard the discussion already this morning in the session that Mauro was chairing with interventions from Isabel and Andrea. Isabel, I see there. I think Andrea's left. And now we also have a couple of colleagues here today from some member state agencies that are going to explain specifically how they're making use of Earth observation. So the first you see there on the list of this first subpanel is Ruben Piroska. Ruben is from the German Federal Office of Civil Protection and Disaster Assistance. He's also the Copernicus coordinator in Germany for CEMS, the Copernicus Emergency Management Service. The second colleague there is Antoine Guyon. Antoine is at INERIS, the French National Institute for Industrial and Environmental Risks. And he is a research engineer in H21 and forecasting. And the last is Matteo Matteuzzi from the European Environment Agency, and Matteo is an expert in the Copernicus Land Monitoring Service. So I'm going to ask them now a series of questions, or some questions for some of the colleagues and some for others. I think I'm going to start with Ruben, and we have for at least some of the panelists one slide which will be up behind them the first time they answer. So Ruben, the first question which I'm going to ask to both yourself and Antoine is how AI and machine learning methods have improved or created efficiencies in your products and services to better address the user needs that you're serving. Go ahead.
So as you see on this slide, we had a research project. It was called AI for Flood Damage, and it's now in the third phase. So we did for 2 years, starting 2024, with research in machine learning to fast identify reliable information about the destruction after heavy rains and floods. So and as you see, it's a research project, so it's not already in an operational way, and the results are very good. So from my perspective, there's a lot of potential for this to be integrated in a kind of a service. So, but it's at this state, it's a Jupyter notebook, and you can click through, and it's not very user-friendly.
And maybe just to ask, what were the specific kind of additional needs that your users were asking that were not available from the core products, and you thought you could address through this? Yeah.
So, yeah, as mentioned, the user-friendliness, like having a UI, a user interface, which is like LLM or something like that, that would be great. But maybe to make it more easier, to have a UI where you can click through, that would be great. And also the integration in existing systems, because lots of users, they have already systems running. And if we start from scratch to give them a new AI method in this and that, then it wouldn't be helpful. So we need to help them to integrate it in their existing systems.
Okay, Very good, thanks. And so, Antoine, I ask you the same questions, or how have kind of AI and ML methods really helped you increase efficiencies and really better address the user needs that you need to address?
Yeah, so we've been using increasingly AI in our workflow for air quality modeling and forecasting. And so we have earned in time, in precision, and also in product coverage. Yeah, I would say that yeah, the ability of AI to process such amount of data, especially in our field when we have multiple sources of data with different resolution, coverage. So it really helped. And if I have to give some examples to show how it addresses in a better way the user's needs, I will talk about also high resolution air quality mapping. So for instance, we managed to do a downscaling of CAM's product that can be really relevant for exposure assessment for epidemiologists. But also another situation is about air quality forecasting. So with AI, we can correct the model outputs and have a better prediction of air pollution episodes that will be in support of the local or national authorities. And finally, also, we use AI to better characterize the pollution, to have source attribution. And we can develop surrogate model, and like this, we can assess from which sectors, which geographical area sources are coming. So this can be really relevant for policy makers.
Thank you very much, Antoine. So with that, I'll move now on to the second question that I'm also going to ask Matteo. I don't have a slide for Matteo, but so we'll leave Antoine's on a little longer. But now this is kind of more, so the question I asked before was more kind of to understand what has worked so far, but now is more looking to the future. So Matteo, where do you see additional opportunities to really better integrate AI and machine learning in general in the products, in your case, of course, products linked to CLMS, and services that you're delivering?
As you know, CLMS is implementing and producing quite a lot of land products, and we are using machine learning since many years. So, but it's methods like random forest, and I don't want to spend now on that application. Rather, it's on vision, computer vision type of things. And I would like to highlight our land cover land use products, which need context for their creation. So it's typically a human interpreter who is digitalizing the products, and which is actually a very time-consuming and full of effort activity. I'm basically wondering if with AI we can develop applications which are capable of interpreting that context and do this type of mapping automatically. This would increase our speed in product timeliness, which is clearly a critical problem for this type of products. Obviously, also the cost effort might go down, and also the reproducibility of the data set itself. So that is, I think, where we as a CLMS would have the biggest potential or biggest improvement in that new thing.
Okay, thank you very much, Matteo. And Antoine, coming back to you, same question. Where do you see the greatest potential in the future as far as kind of looking to additional developments?
For the last years in our field, AI has been mainly used as a post-processing step. Like I see it like an additional layer, and I think that a lot of opportunities are also in the generative AI, as this morning also Matthew mentioned with the example of AIFS Compo for the atmosphere. Yeah, to include it like a proper approach and not like another step, but still, of course, it has to be in complementary with the physics-based approach to keep control also on what we do and to still for research understand the processes. And yeah, there is this for the generative AI, and also another point for the opportunities is about the interpretable AI also. I think that is important with those neural networks architectures that are becoming more and more complex. I think that we have to put effort also in tools able to interpret the results and to understand how the model works, to keep control it and to maintain it in our workflow of quality control. Yeah.
Okay, thank you very much. And then finally, Ruben, back to you on the same question. So, you know, as you said, up to now, it's largely been a research project that approach, but really, where do you see the potential in the future, especially in your area of application?
Yeah, so I think for disaster management, for disaster protection, early warning is always a big issue. So if we use machine learning in early warning systems, like identifying that the pattern, what is unusual, to create maybe an alert, I think we're far away from creating autonomous alerts, because this is maybe difficult. And then I see also that what we heard this morning about DestinE, so the what-if scenarios. These are really interesting because the cities, they are interested in what would happen if a flood wave with 10-meter height would hit the city of Bonn, and then the decision makers can be prepared for that upcoming flood wave. So even if the event is not happening, they have like a scenario which they can play with. And also maybe kind of simulation or training would be also interesting, to have like machine generated disaster risk, disaster training. That would be also very interesting to see and integrated in maybe in SEMS.
Yeah, excellent. Thanks very much. And it reminded me, especially at the urban scale, we did an assessment last year in the KCO on urban climate adaptation. And I think of all of the assessments we've done, that was the one where it was very clear to me that a lot of the users are needing both Copernicus service output, but also the DestinE kind of what-if type capabilities you just mentioned. Okay, so the last question is specifically for Matteo, because I think, Matteo, you have kind of taken a fairly strong initiative in CLMS over the last couple of years in building up the discoverability options to access data through Observia and other initiatives. I know that there's now a discussion across all of the Copernicus services, you know, how we kind of generalize this approach in Copernicus to improve the discoverability of data and products. Maybe do you want to explain a bit that process and what opportunities you see, or increased opportunities you see in the future to really improve that discoverability and access to our data and products? Yeah.
Yes. So I will really stick to discoverability and not going to AI analytical capabilities. And in fact, all this has started with a survey which we had launched in 2023. Where we try to understand about the user uptake of our products, and we have tried actually to understand also the struggles, why users eventually are not taking up our products. I think the outcomes were very interesting, and there were a few very basic or down-to-earth issues, like we simply cannot find your products. And here I will always remember a colleague from my time when I worked at the university. Matteo, you at the CLMS, you're doing nice products. I was not aware. And we are talking about somebody at the Institute of Geomatics, so basically fully into the topic, not being aware of what we were doing. So this is, I think, a very important concern. And then also, our products are partially very complex. So in order to use a product, you need to be able to understand the product. And what we basically left our users, okay, there is the product user manual, 80 pages, 120 pages of complex text information. There are the ATBDs, another even more complex information. So in line of, we saw the opportunity of LLMs, which were quite prominent at the time. And basically we have set up this Observia chatbot, where the idea is nothing else that a user has a requirement and asks what data can we use. And then it points to the proper data that can be used. And then if a user wants to understand how this product is, how it was created and what information it contains, it can specifically ask that question and get the specific reply without the need of reading this 100 and more pages of more pages. So, and this is led to this Observia chatbot. Parallel to that, we also started to make our technical information, so these documents, more accessible to internet crawlers, so indexation, so that it can be found also by other LLMs, because we want also users of other LLMs to find our products. That is obviously the goal. So I think we managed to harness an important opportunity what LLMs gave to us in terms of data discoverability. And I think the next step here is a chatbot where you need to think. I think Earth observation is at the end something that is reserved to specific applications, to specific needs. There is a lot of complexity in producing and creating this data, in extracting information about this data. Now you need to imagine a chatbot where you just ask, or you are just a citizen, where you want to go to live somewhere, and you ask, what is the flood risk in my area? What is that house that is, what I'm interested, is that in a particular heat island, or things like this. So basically the chatbot, which is capable of understanding the requirement, knows about the data, knows how to process the data, and delivers the output to the user. And I think this is the way to go, and the big potential to basically make use of LLMs. And tomorrow in the booth I will present a prototype.
Actually, that gives me the opportunity to say that all three of our first panelists tomorrow will have things in the demonstration area. So please do take the time to pop by and see their demonstrations. So thanks for that very much, Matteo. So maybe I'll just pause here for a moment to see, first of all, if there are any questions from the room, and also to ask Nori, is it you who's following online?
There's one.
Okay, first, I'll just check in the room first if anyone would like to ask a question to the first three panelists. No? Okay, Nori, do you want to?
Sure. So the question was specifically for Ruben, and I'm paraphrasing, but how difficult is integrating new products into existing solutions, and does AI help in this process? Is it making it easier?
So I want to be humble. I'm not an IT nerd. I'm a AO nerd. So I think if you have a good roadmap to know what is your process already, existing process, if you know the infrastructure well, if you have good documentation, then you know where you can integrate the new product. So this means it's like Mattia also said, you need to be aware what you want to do with AI. It's not just using the buzzword AI. You have a specific need, and then you need to identify it, work with someone together, or you can do it on your own, program it, and then you can integrate it because you already know your infrastructure. So this would then help you, because if you just start developing something and it might not access the need of you or your users, it might also not make it to an operational way. So think before starting with your project.
Okay, thank you very much for that, Ruben. So I think we'll move on now then to our second set of panelists. Yeah. So we have, now that you remember we're kind of transitioning now more onto topics that are around this idea of trustworthy AI, and specifically addressing also ethical AI solutions. We have 3 additional panelists for this segment. Stephanie Lumnitz, who is a policy officer actually here in DGRTD in Brussels. Hannah Koffler, who is the project manager for image processing and data science at Constellar, and Alistair Francis, who is the co-founder and partners at Asterix Labs. And I have some slides for them as well. I think actually I need to skip over Hannah quickly because we're going to start the questions with Stephanie, but don't worry, Hannah, we'll come back to you. So yes, again, 3 questions that I'm going to ask 2 of you on each question. The first is this kind of almost cliche of the black box and the black box stigma. So how do you kind of suggest that we should be mitigating this with respect to our users? And what are kind of cautionary points on data veracity, reproducibility, and trustworthiness? And I'll start with Stephanie.
Okay, thank you very much. And hello to everyone also from my side, from DG Research and Innovation. So I'd like to start answering this question with a comparison example. Some of us decide daily to step into public transport, into buses that other people are driving normally for us, without knowing how a combustion engine actually works. And we still sort of like, maybe at the beginning, trusted to bring us somewhere, and then with experience we know it's gonna bring us somewhere. And I think for AI, we are in a similar situation that we have had complex models before. And the way how we have aided building trust into complex models was also in the past to follow existing scientific practices and standards. So follow transparency in data. I think in Europe we are really well suited for that because we have many publicly funded high-quality data sets such as ERA5 that also big tech now builds their services on top. We know roughly for AI that we have to build robust models. Nowadays there is a lot of community standards that show us how to do this from a technical viewpoint. But also we know that there is evolving concepts such as hybrid modeling or embedding AI systems into, let's say, physical constraints. So also here we have great examples that the community already has provided. For example, the Horizon Europe funded project AIRI that used machine learning to emulate expensive components of Earth system models. And then as a side effect also achieved better computational efficiency for certain parts. And then lastly, we also already know that as a scientific best practice, we have to ensure reproducibility, even if not on the bit reproducible. But in any case, having reusable models partially as well. And here, of course, we have these great programs such as DestinE or Copernicus that help us building this ecosystem. But we also have the Use AI in Science strategy that, for example, is also strengthening the scientific ecosystem around AI, not only in Earth observation, but many other fields. Also here connecting data infrastructures, so bringing the user to the data, to the compute resources. We've heard about the gigafactories today. And then also allowing, let's say, genuine reproducibility and reusability with similar system components. So to conclude, I think AI, like our public transport buses, really become trustworthy, or also basically not black boxes in a way anymore, trusted black boxes in that sense from users that don't do AI development. If we ensure that AI is part of a reproducible and collaborative scientific process, and that these standards that have guided our research in the past also continue to guide our research in the future.
Thank you very much, Stephanie. I noticed that you kept the drivers in the buses, which may, once we don't have them, may add another level of complexity to the analogy. So I'd like to now move on to Alistair. Alistair, the same question to you, and anyone that has a motto, a trustworthy API is a prerequisite for trustworthy AI, I think is well positioned to address this session. So again, Alistair, this first question is really around how we mitigate this kind of general stigma that seems to be associated sometimes with AI on being a black box.
Yeah, I mean, Stephanie, her analogy with the train driver is excellent, and I had a very similar one prepared, which was the human brain. And, you know, we trust other people that we know with a great deal of you know, incredibly important decisions that they make around us. And the reason that we do that isn't because we can see the neurons in their brain and we understand how they're making their decisions. We do it because of a social network of trust that's been built up in society, right? And so the scientific method and reproducibility is a really important, you know, component of that. And I think to add to that as well is the kind of the networks of trust that already exist between data providers and users, and making sure that you kind of leverage those networks of trust to make sure that your AI solutions respect that relationship. So I suppose one of the things that we've been thinking about a lot at Asterisk Labs, so we're a small research lab, and one of the things we did was last year we prepared a report for the ESA Copernicus office about the kind of future vision for the Copernicus data ecosystem in light of AI. And one of the kind of worrying, let's say, trends or possibilities, possible worlds that we could end up in is if the institutions let go of that link between their users and the data. So if users start to get their insights from a kind of third-party platform with no kind of affiliation to that institution that provided the data, and I assume this might also hold true for private data providers who also have a relationship with their users. The danger is that we end up in this kind of opaque world where people are getting information that are derived from, let's say, Copernicus data, but there's no way of, as Steph is saying, reproducing those results with the open model, right? Having an API that is actually, you know, maybe not everyone goes and checks the model weights, but some people do, and they work out what's going on. And yeah, well, I think the message I would give is to build trustworthy AI, people, you know, institutions that are data providers like Copernicus that have built this incredible trust with their user base over many years of providing, you know, the highest quality Earth data there is, need to be in the room when we're developing those AI solutions, not leaving it up to a big tech company to kind of make that value-added layer on top. We need to think of it as a core part of those institutions' data offerings. And then that enables a kind of trusted ecosystem on top of it where all sorts of people can do all sorts of wonderful things, but we need to make sure that those, you know, and I'm really talking about kind of embeddings of data which lead on to all sorts of other applications. Those embeddings are made in a way that maintains trust between the original data provider and the user base.
Yep. Thanks a lot, Alistair. I think, well, at least for me, that really resonated a lot. Some of the discussions, and Matteo has been a part of this as well, that we've been having on this type of discoverability aspect, that key element of how we maintain the interface between the authority that the Copernicus services have developed over the last 10 years or more in many cases with their user base in the context of kind of AI discoverable scenarios is something that I think many of the Copernicus services feel very strongly about. So I can see if from your perspective that's key as well, then that's something we definitely need to think about how as we're implementing these tools. Okay, so I'll move on now to the second question, and this gives me the opportunity now to move back to Hannah's slide. Hannah, I'll start with you on this, and I'd like to ask it to Stephanie as well. Oh, by the way, I didn't mention the first three panelists. If you want a chocolate, you did very well. You can take it. So yeah, I'll start with Hannah on this. And this is really about how we build trust in AI-powered products and services. So that process of actually the dialogue with the user base and how we're providing AI-powered products, how do we kind of communicate best practices, lessons learned, the open data aspects, or not in some cases for very good reasons, and how we foster kind of adoption of this. So Hannah, over to you.
Yeah, sure. Maybe I'll need to quickly explain who Constellar is, because probably it's not known by everyone. So we're a new space company, and we're providing high-resolution thermal data from our own space assets. We currently have 2 satellites in space delivering high-resolution thermal imagery like the one on the slide. So generally, I think we're obviously more part of the upstream, like we're a data provider into models, and we believe thermal is uniquely placed in being an important aspect and an important input into modeling and AI models, because thermal is a physical reality. It's heat and it's energy, compared to maybe a visual or a SAR data set that's more appearance and structure. So we think for AI models, thermal is super, super interesting, and it can be modeled. There is diurnal cycle models that can be applied, and we're also obviously looking into that. Generally, we think as a new space provider, Copernicus still sets standards and still sets baseline data sets that people can trust in, and we as new space need to build that trust as well with our users. Our data set doesn't have a 10-year archive, doesn't have that legacy, so we obviously need to follow those kind of proven best practices of how do we communicate about our sensor technology, how do we communicate about our processing chain, how do we communicate about what our data can do and what it cannot do. And here we are following those. We are part of some initiatives, obviously. We are part of the Copernicus contributing missions in a Category 1 contract, so our data is currently being evaluated for how this can be integrated into future Copernicus products. We have a contract with the European Space Agency. Our data is available for non-commercial projects via a third-party mission contract. So we as New Space play a role in here as well. We bridge a gap in providing data that is not available via the institutional missions, and thus are, let's say, complementary to what is there, and sometimes we're able to provide a data set that is actually not available. And that should not be forgotten. So far, I haven't heard anybody talk about New Space today, so I'll try to bring that message in as well. New Space is there, and it can provide good quality data that can be also integrated into those models.
Excellent. Thank you very much, Hannah. And I'm sure that maybe it needed you to come to the stage and make this case for new space, but at least in general, I think both within Copernicus and DestinE, the role and value of new space is well recognized. So I'll continue, Stephanie, with you on this as well. If you could provide us your perspective as well, and really how we build up that trust in AI products and services.
Okay, so thanks for this question. I think we could talk about this for hours and hours. So I would really like to build on top of what Hannah said here, because we are an Earth observation and artificial intelligence community here. And I think it's very important for us to not forget and to communicate properly what does the data we use as the baseline of this data-driven developments actually represent, and what is the availability of this data. And I give an example from work in Horizon Europe and also in other places. So often we hear, for example, about urban heat islands, services and products. And then they are communicated as urban heat island services and products. But if you look into the details of what do these products and services actually provide, in the past, very often we've seen that they have used land surface temperature measurements from satellites, where sometimes, Hannah can maybe explain it to us better, even the temperature measurement is a complex modeling process. And we sell urban heat island services that in fact only represent land surface temperature and not even ambient temperature of the urban environment. So I think for us as a community, it's very important to go back to the basics of environmental observation and basically really communicate clearly what does this data that we do predictive development with actually represent. And then, you know, if we can, for example, include urban climate models that help us, or in situ data that helps us interpret better the temperature measurement of ambient temperature, then use, you know, the correct term, which is urban heat island. So I think this is like a call also to us to be clear about this data representation. So this is the first thing that I think we need to do better in communicating to build this trust. And then the second thing is also the availability of this data. So we know that, ESA puts it, taking the pulse of the planet is an approximation. So we are not measuring everything. And the question here often is what, let's say, key observation gaps, for example, remain to really be able to make these urban heat island predictions. So, and that's basically maybe a bit of the future work to do for us in this new paradigm of data-driven developments. What, let's say, data representations do we still need? And this is also partially, for example, work of DGRTD together with international science bodies like IPCC or IPBES or international organizations like GEO to properly map where are these, let's say, representation gaps that we need to still fulfill certain user needs and requirements.
Okay, thank you very much. Did you want to answer anything that Stephanie said?
I can complement a bit. Yeah, I mean, urban heat islands are definitely a topic that constantly comes up when you talk about thermal data. There's definitely research ongoing. So how does air temperature relate to land surface temperature? Are those two related? Can they be correlated? We did have a project as well that talked about I think it was called Human Comfort Index, where we proved that the LST is actually quite well related to that. So, I mean, it's a big topic, I think. It's being tried to, let's say, research from different angles with different data sets. But yes, I mean, on the baseline, you need to understand what your baseline data set is. Land surface temperature is land surface temperature. It's not air temperature. And so, yeah, it's crucial that we have the terminology, that we know what data is ingested.
Okay, thanks. You can pass your mic on to the end, to Alistair now. And so we're coming up now on the third question, which I'm going to ask to Alistair and to Hannah. And this is really about the approaches and AI solutions you see you implement at the moment to help quantify, communicate, and manage uncertainty in the AI-driven results, including on the transparency and model limitations, which you've already addressed to some degree, but I think it's really about this communication of uncertainty is the key element there.
Yeah, I mean, maybe you can just, for context, put my slide up, because I was just going to briefly touch on an upcoming project that we have that's relevant to this. I mean, so obviously, when you talk about specific methods to communicate uncertainty, there's basically every single application of AI is going to have a different way of doing that, right? So we're really, really focused on compression at the moment in Astris Labs, and the reason we're focused on compression is because we think that to make the most of open Earth data, this incredible resource that we have, it's so large that it's both a blessing and a curse, right? And so compression is really like the first step to enabling and accelerating all the other people who want to do wonderful things with the data to be able to do it cheaply, for a small research team to be able to work with global data at scale. We think compression is kind of the key bottleneck there. So the good news for me is that compression is very easy to talk about traceability and uncertainty with, because you're training on your targets, right? So you just have to send it through the model, reproduce what went into it, and make sure that the pixels aren't too dissimilar from when they went into the model. But obviously it goes further than that, and so what we're thinking about in this upcoming project, Earth Compress, is to develop an open source set of tooling, a sort of set of protocols for data providers to use. We're not kind of building our own platform for data to sit on, we're really thinking about tooling for data providers to use to enable them to compress their data and to serve it to people in a way that is traceable and trustable. So if a user says, I'm okay with this much error rate in my pixels, whatever metric, then you can serve embeddings that give them that error rate when they decompress it on the client side. So the idea would be, you can choose your compression rate and therefore your bandwidth acceleration on transferring of the data. And as we heard from the talks from ECMWF, from Tiago, and from Cloudflare, like just transferring data is a very non-trivial part of anyone's workflow now. Even if you're working on cloud, opening the data is a nightmare still. So we're really, really focused on this and kind of building up this, as I say, protocol that basically gives users the kind of knob to control how much compression they want and how much loss they're willing to take. And we really think that is, we're developing that as an open source toolkit because we really think, as I mentioned in my previous answer, that data providers have to be at the heart of that initiative of providing AI embeddings of their data. If someone else provides it, then there's always room for mistrust, because going back again to the brain analogy, the human analogy, you'd be trusting a stranger versus an old friend, right? So we really want to give the old friend the tools they need to keep up with the new needs of the users, where they want scaled global data that the current size of the data doesn't allow for. But yeah, so going back to trust and traceability, I think for us it's been fairly straightforward to define those metrics because we've got the targets that we're training on. For other people, I think in like the urban heat island world and others, it's much, much harder to try to reason about the uncertainty that our model's producing.
Although, can I maybe add on to that, Alistair? I mean, I understand this idea of having this kind of knob, but what happens, I mean, I suspect in many cases the person turning that knob is a lot upstream on the data production value chain, whereas then how do you then propagate that to the final user?
Yeah.
And his knowledge of how much the compression has impacted.
So this is the great thing about compression as a use case, right? It's fully provable and reproducible. So the basic idea with Earth Compress is that a user will download a set of model weights that is the decompressor on the client side, okay? On the server side, there are a set of embeddings of the data that are sort of compressed representations of the data that are given to the client side, but they also come with a kind of metadata quality flag saying, hey, if you were to decompress this data, you get this error rate on average over the pixels with these metrics. The user can go and do that with the decompression algorithm, right? And they can look at the original data. They can even go and download the original data for a set of samples and check against the decompressed versions that their model has produced on the client side. So in terms of trust and traceability, I think compression is a really nice use case where you've got this kind of closed loop between the input data and the output data, and you can really like verify the full chain when you have the client side that has the open model. Obviously, if it's a closed model and you're just getting embeddings from some API and you just receive some vectors that you can't then decompress and inspect, things get a bit more tricky to validate.
Okay, thanks. And finally, so I'd like to ask everyone to start thinking of any questions for these three panelists, but we have, finally, I'd like to also ask Hannah to address this third question really on, in developing your AI solutions, how you communicate this any uncertainty associated with the AI-driven results.
Yeah, so as I mentioned before, thermal is something that can be modeled. So we also provide, in addition to the proprietary data sets from our satellites, a thermal modeled data set where we ingest publicly available data, like a data set from CLMS, MODIS, WIRS, Landsat, and our own data set, and try to provide a continuous land surface temperature data set that has theoretically an output every hour, but we don't provide every hour. That would be a bit much data, but right now it's, if somebody would like to look at that data set, it's an output every single day at 11 a.m. And obviously, we do not have high-resolution observations every single day, but the data set itself is always, the GSD is 30 meters. So what we do is we provide a quality layer in the product bundle where we describe on that specific pixel how close it is to a high resolution, how close it is to being derived from a high resolution data set, or if it's a pure modeled output, or if it's based on a very coarse resolution data set like CLMS. So that is all, let's say, public on our knowledge center and described on how we have derived or how closely that pixel is to a true measurement of that pixel size, so to speak. So we're quite transparent about that. What is a model output? What is derived from a true measurement? And I think that's the transparency that we need to provide so that people can understand how this data set came to happen, because everybody knows there is no land surface temperature product that provides high resolution data set every single day.
Okay, thanks a lot. So any questions from the audience to this? Okay, I see 2, 3. So if you can first maybe go up that side, Stephen, and then we'll go to Carlo. Is there? Can I see any other hands? Just I've seen the 3. If there's any more, okay. So we have. If you can go over to Carlo. There were two there. Either you pick.
Yes. Thank you. I would have a...
can you please introduce yourself first?
Oh, sorry.
So, yeah.
I'm François de Vieilleville. I'm working at Genome Space. We are an SME company doing AI and putting AI on board of the satellite. So my question is for Alistair Francis, for the compression. We all understand that it's immensely huge advantage and it's really nice. But I have somehow a naive question in the sense that usually in signal processing, when we make, say, not discoveries, but let's say we understand better the signal than what we have, it often relies on the weak part of the signal. How can we ensure that we keep this weak signal when we have compressed the data so much that all of a sudden it can be very democratized and used? So this is important. So.
Yeah, that's a great question. I think there's multiple ways you can approach compression as a sort of learning problem in ML. The basic case is, fit the data into a compressed latent space and then decompress out to the original targets. That tends to work pretty well for image data because there's a lot of redundancy in spatial information, right? Just naturally, gradients flow quite slowly through an image. You end up being able to compress quite a lot in that way. But of course, you know, just as an example, a project I'm working on uses the error, well not error, but the parallax effect of the Sentinel-2 bands and the rainbow effect that has on clouds to measure the height of clouds. Probably a compression algorithm will throw away the clouds, right? Because clouds don't seem like they're important to most users. So the real key there is to have a kind of zoo of different pre-training tasks that you would use in your compression, right? That are kind of linked closely to different downstream user groups that would be kind of defined in like a co-design phase with the data provider, right? So the data provider would go out and find their key user groups. They would work out like, you know, what is it that's important to you? Maybe the task would be, let's take Sentinel-2 again as an example, is actually not projecting back into Sentinel-2, but we want to also be able to project into Sentinel-1, or we want to be able to project a different part of the time series of Sentinel-2, whatever. And so you can promote different parts of the semantic space through those different pre-training tasks. Ultimately, it's not a science, it's an empirical kind of trial and error. And so the key really is transparency and making sure that users have the tools they can to test themselves what's working and what's not, and give them a diverse set of options.
Thanks, Alistair. And the second question?
Yes, I have a question that is a little bit more general, because the panel was about uptake and AI, and I was wondering whether you have a sort of an idea of how the current change in like the whole crisis of software as a service, and the idea that software should be like pizza, done on the spot and consumed immediately. This is a change of paradigm. That kind of what you say about trust, because it's not very obvious or immediate, because you can look at futures where clients don't care if the end result is usable. They don't care how they got there. And on the other hand, trust will be resolved with sometimes going back to analogous solutions, or like sending a fax so that I know that the government is going to accept this as a proof. So we can imagine these sort of very extreme results of the current changes in the whole software production paradigms and use. Do you have any inputs on that when it comes to trust?
Go ahead, Alistair.
Well, I think if I understand your question, I think you can think of AI as software that is not derived through sort of human priors, but derived purely from the data, right? So AI is kind of software based on the sampling distribution of data you have. So to me, ultimately, I think when, you know, as I always say, compression is kind of an easy case, but when you move into harder cases, the trust ultimately is going to have to come from understanding whether you are in the correct distribution of your data space to begin with in the inputs, right? So are you asking a sensible question of the model, or are you kind of in a part of the landscape that the model doesn't even understand? And then also kind of understanding, you know, the biases and the priors that the training data set imbues within the model, in the same way that faulty software is imbued with bugs from its developers. You know, hallucinations of LLMs don't come out of, they're not some kind of purely imagined thought. They're actually, you know, the shadow of a distribution in the training data set, right? When the model's not sure of how to answer you, it falls back on some prior that it finds in the training data set, and that's what hallucinations are, right? So maybe that's not answering a question directly, but it's kind of saying that I think you really need to ground yourself in the data when you're thinking about trust with AI software.
Yeah, no, I agree. And the traceability back to that data, I think, that was used in the training is relevant. I remember back in the 1990s when we were working first on neural networks, understanding that the distribution functions of the input data were kind of gave you boundary conditions on what you could actually ask the neural net to be doing was something that completely changed the performance of those neural nets. So I think that, yeah, in an abstract sense, it's really about the traceability back to what the original data is covering as far as distribution functions. Very good. Carlo.
Yeah, thank you. Carlo Buontempo, C3S at ECMWF. Well, actually, my question is related to the discussion we were listening to between Stephanie and Hannah on the data. Because it seems to me that there is a fundamental question that AI tools are posing on the upstream. In a sense, are we observing the right thing? Or should we observe something different? So what I would like to ask you is, what do you see the new challenges in terms of observation are to respond to the AI landscape? Thank you.
Stephanie, you want to go first?
Sure. So maybe I can give a perspective, so not a complete one, but an approximate one. So at the moment, we see that many of our AI systems, as have, by the way, past services as well, built on top of, 20-meter, 30-meter resolution from Landsat and Sentinel. And we know that many of the problems we are trying to tackle, given, for example, in the urban sphere, 20 to 30-meter resolution or information content from pixels is often not serving all of our use cases. So, for example, how do we make decision on whether there should be trees planted? How do we make decisions on how the air quality is? If partially we can't observe these things. So I think number one is really starting to leverage more capabilities also from new space. And I think it's great to see that also here calibration and validation activities are taken up from best practices, for example, of, let's say, the older space components. So this, I would say, is one. So asking the question, what resolution space does my problem actually have? And then second, I mean, now it gets maybe a bit political, but we also do see that there is a geographic distribution of information. So maybe not so much with Copernicus, but we know that most applications do also have to, for example, in weather forecasting, they have to also take on board in situ measurements, other types of data sets in ocean observation, right? We rely partially on Argo information. And because of changing contexts, of course, there also we have access or we don't have access to certain types of information. So also taking into account that maybe all of a sudden there's an information pool we don't have access to anymore, and preparing for these cases in specific situations. I would say that's a second one to look out for in the next couple of years.
Yeah. Just, Hannah, before you come in, I mean, I also took Carlo's question, but maybe I don't want to misinterpret you, Carlo, but I also took it other ways that we can use these methods and these type of analyses to actually emerge these missing observation data sets that we don't have present. And I can see that. I mean, if we're saying this is a kind of a data-driven paradigm that we're in now, and we have reference data sets, a lot of mention to ERA 5 today, but many others as well. But, you know, we should also be able to use, almost to reverse engineer this process to understand what are those missing training data sets that were. So yeah, I'm not sure we're going to answer that today, but to me, is that what you were getting at, Carlo? Yeah. So yeah, I'm not sure we'll answer that today, but I think it's a very interesting point and something that maybe we should think about how as a community we kind of look at that as well. Anyway, Hannah, over to you.
Yeah, sure, I can maybe like say complement a bit what has been said. So when we talk to customers and we have 30 meters data, yeah, that's great, like that's the most high resolution thermal data set. Then comes the question, oh, can you do 10 now? Like, the resolution just is currently, it seems, a game to be played. We think resolution doesn't solve all of your problems. It's still a question, what are you trying to see? What are you trying to prove? What are you trying to do with the data? And I think, like, Earth observation data is an amazing data set. So much can be derived from it, but to get to a ground truth, or to prove that you can see something, yes, ground truth data is needed. If we say there is a hotspot somewhere, we cannot tell where that hotspot comes from. It could be anything theoretically, so you need always additional data sets to really derive and find the truth in the data. And I think that's applicable to, general data science on how do you derive the truth from what you're trying to look at. So resolution is part of it, maybe in some cases, but not always necessarily.
Okay, thanks. I'd like to see if we have one or two questions online. Nari?
Yeah. So I've got a few questions.
Maybe pick your top two, Nari.
Okay. So I think this is for all the panel. So the question or the comment is, so far there has not been much mention of actual user research grounding the development of AI services. Can any panel members discuss the role of practical user research in what they do, or their ambitions for user research going forward?
Maybe Antoine, can you say anything about that? I understood for a lot of your applications, you have a national user community, so you must have a kind of a dialogue with them on this, and how kind of the AI improvements that you have integrated have helped better address those needs.
Yeah. So we have dialogues, and we can try to see where products are needed, and work in that field. I just give some example previously about the air quality data at high resolution that we can provide for exposure assessment for the epidemiologist. So now we are, for instance, working on the main regulated pollutants, but also in epidemiology, or going to new products, focusing on other pollutants, other species. And with the AI, I think we can and we would like to extend a product of exposure. I don't know, for heavy metals, for instance, but it's true. It's important, especially in a operational system like us. It's important to use AI in order to match with the users needed. Yeah.
Yep. Okay, thanks. So yes, go ahead, Ruben.
And thanks to that question, because it's really good. 2 weeks ago, when we had the workshop, DG DEFIS meant Copernicus still is user-driven, so this means we can't sit here in our box and do something which is in our eyes good. So from my perspective of a SAMS coordinator, when I do training, and to underline Matteo's really high valuable work, when the Observia came up, we promoted it, and we said, look, there's something new and you can use it. So this means we need to keep our eyes open, what's happening in the context, in our context, and to promote it. So, and for Observia, it helped to improve it, because we gave feedback, and then this worked. So, and now users, they can use Observia and ask in their language. Before it was English where the best answers came up. So this shows it's user-driven.
Yeah. Yeah.
I can maybe add something as well, like as the commercial representative maybe. I mean, in the end, for our customer interactions, our customer asks us to solve a problem for them. If this problem is not solved by AI, if it's solved by other tools, if it's solved by very basic data science, is not really the question. It's the question, is the problem going to be solved? So AI can support that in making it cheaper, can support that in making it the outcome better, et cetera, but it's not for the purpose of AI. So I didn't want to, let's say, go away from the AI discussion of this panel, but let's say for a user, in the end, they want to have a problem solved through whatever the means is to solve the problem in the best way.
Yeah. And by the way, that's not just a commercial perspective, because it's exactly the same point of view we see in the work we do on assessing policy requirements. We are normally completely agnostic of the solution at the beginning. So it's just about understanding what the needs are and then looking for the best methods and tools to assess that, of which one important tool, which is becoming everly important in our toolbox, is of course AI and machine learning methods. So Nori, do you want to give us our last question?
Okay, it's a pretty broad question, and I'm paraphrasing again, but I mean, there are a large number of AI-enabled EO platforms and services emerging. I mean, we've seen quite a number of them presented today. But the question is, how does a user select amongst the various options?
Okay, I think I'll give that to Matteo. In a sense, it's...
Ask the chatbot.
Yes.
Which one?
I think we are used to an environment which is fragmented. This is, I think, a problem. And what we should aim for is comprehensive solutions which are capable to go beyond this fragmentation. But I don't see necessarily the problem in having a large variety of options. So on one hand, I think it's good to have options because they are specialized on something, but I see the problem rather being a back-end issue. If you only can access parts of the data because your catalogs are not talking to each other, the thematic of interoperability and of federation, this is the issue. On the service side, maybe some competitivity is not the worst thing. So,
yeah. Okay. Thanks a lot, and thanks to all of the audience online and here for their contributions to this session as well. I'd like to ask you all to join me for a round of applause for all of the panelists and for our speaker. And since we started 5 minutes late, Mitch, I don't think we did too bad. So we can have, actually we're going to finish all your chocolates. And I think I'm asking Daniel to come up now, who's going to give us some wrap up for today and preparations for tomorrow.
I hope you had an amazing first day. Really happy to see so many people here. Special thanks to all of our speakers today for the insightful information that we saw. For the people in the room, please don't forget your badges because you'll need them tomorrow. There are also some sandwiches left, so if you want to eat before you leave, feel free to help yourselves. For the people online, sorry, sandwiches are only physical, so nothing virtual for you. But thank you so much also for attending. We were impressed by the high number of online attendance. Link is the same, so see you all again tomorrow, same time, same place, and hope you will have an amazing day as well tomorrow. Thank you everyone on behalf of the organizational team. Thank you.